In the late 1990s, astronomers made an observation that fundamentally challenged our understanding of the cosmos, discovering that the expansion of the universe itself is accelerating rather than slowing down as gravity would suggest it should, and this acceleration appears to be driven by something we cannot see, measure directly, or explain through any known force in physics, something we now call dark energy, which comprises approximately 68% of all matter and energy in the observable universe, yet remains entirely mysterious and beyond our current scientific comprehension. The evidence for this acceleration came from observations of distant supernovae, which appeared dimmer than expected at their calculated distances, indicating that space itself was expanding faster than our models predicted, as if some invisible force were pushing galaxies apart from one another on scales so vast that they dwarf the gravitational attraction between even the largest structures in existence. This discovery fundamentally altered cosmology because it suggested that nearly 7/10 of the universe consists of something completely unknown, something that violates our intuitive understanding of physics and challenges the very foundation of how we interpret gravitational interaction and cosmic evolution. The psychological mechanism behind our acceptance of dark energy lies in the gap between observable reality and explanatory power, where we encounter a phenomenon so consistently verified through multiple independent lines of evidence that we must accept its existence despite having no coherent theory to explain it, creating a peculiar situation where consensus is built not on understanding, but on the weight of reproducible data that refuses to align with established physical principles. Imagine observing the cosmos through our most powerful telescopes and discovering that approximately 85% of all matter in the universe remains completely invisible to every instrument we have ever created. Yet we know it must be there because of its gravitational effects on the visible matter we can actually see and measure. This is the peculiar reality of dark matter, a substance so profoundly invisible that it leaves no electromagnetic signature whatsoever, reflecting no light, emitting no radiation, and absorbing nothing that we can detect with our current technology. When astronomers calculate the rotational speeds of galaxies and observe how stars move within them, the mathematics reveals an undeniable truth. There must be far more mass present than we can account for through ordinary matter alone, yet this invisible mass announces itself only through the invisible hand of gravity pulling and shaping the visible universe around it. The psychological mechanism underlying our acceptance of dark matter stems from a fundamental cognitive shift in how we approach scientific evidence, for we have learned to trust the mathematics and indirect observations more than our direct sensory perception of reality, recognizing that absence of light does not necessarily mean absence of existence. Throughout human history, we have believed only in what we could see and touch, yet modern physics has trained us to embrace invisible forces, invisible particles, and invisible structures as equally real components of existence based entirely on their measurable consequences. What remains peculiar is how thoroughly we have normalized this extraordinary circumstance without experiencing the profound conceptual vertigo it should perhaps inspire, accepting that most of the universe's mass is fundamentally unobservable and unknown in composition. Yet we continue building models and theories around its presence as though its nature were settled and understood. When in reality dark matter remains one of science's most humbling admissions of ignorance, masked beneath layers of mathematical sophistication and institutional confidence. In October of 2017, astronomers detected an object moving through our solar system at extraordinary velocity, and what made this discovery profoundly unusual was not merely its speed or its interstellar origin, but rather the peculiar way it accelerated in defiance of conventional gravitational explanation. The object, named Oumuamua, which means scout or messenger in Hawaiian, entered our cosmic neighborhood traveling at approximately 26 kilometers per second relative to the Sun. Yet as it passed through the inner solar system and began its departure into the darkness beyond, telescopic observations revealed something that should not have been possible according to our understanding of physics. The object was accelerating away from the Sun faster than gravitational forces alone could explain, exhibiting what scientists termed non-gravitational acceleration. A phenomenon that suggested some form of propulsive force was at work that we could not identify or measure directly. Our conventional models predicted a specific trajectory based on the sun's gravitational pull, yet Oumuamua deviated from this predicted path in ways that indicated it was being pushed outward by something we could not see, and this invisible force continued to propel it throughout its observable passage through our solar system. Astronomers proposed various explanations ranging from outgassing comas similar to those found in comets, to hypothetical solar radiation pressure acting upon a peculiarly shaped object, yet none of these theories provided complete or entirely satisfactory answers to what was actually accelerating this interstellar visitor. The deeper psychological mechanism at work here involves our reliance on visible, measurable, and reproducible phenomena to construct our scientific frameworks. And when we encounter something that behaves in ways our instruments cannot fully explain, we experience a profound cognitive dissonance that compels us to generate increasingly complex theoretical solutions. On August 15, 1977, a radio astronomer named Jerry Amon was reviewing data from the Big Ear radio telescope at Ohio State University when he noticed something that would haunt the field of astronomy for decades to come: a narrow-band signal of unusual strength received from a region of sky near the constellation KIC Sagittarii, a signal so remarkable that Amon circled it on the computer printout and wrote the word "wow" in the margin. A reaction that would become the signal's eternal name and the source of one of science's most persistent mysteries. The signal lasted only 72 seconds, arriving at frequencies that would be consistent with intentional extraterrestrial communication. Yet when astronomers attempted to relocate and reacquire the signal in subsequent observations, it had vanished entirely, leaving behind only that single measurement and a profound absence of any confirmatory data, despite decades of searching the same region of space with increasingly sophisticated equipment. The characteristics of the WOW signal suggested it was narrowband and extremely strong relative to background noise, properties that natural astrophysical phenomena rarely produce in such concentrated form, and its apparent movement across the telescope's receiving array suggested a point source rather than a diffuse emission, lending credence to theories of deliberate transmission rather than stellar accident or instrumental error. Over the following decades, astronomers have proposed numerous explanations for the signal's origin, from reflected terrestrial radio broadcasts bouncing off space debris to unknown natural cosmic phenomena yet to be catalogued by modern science. Yet each proposed explanation carries its own implausibilities and limitations, leaving researchers suspended in a state of perpetual uncertainty. Among the most perplexing phenomena in modern astronomy are fast radio bursts, transient signals that flash across the cosmos with extraordinary intensity, releasing in mere milliseconds the energy equivalent to what our sun produces over several days. And what makes these events even more enigmatic is the discovery that some of them repeat, defying the initial assumption that they were singular catastrophic events occurring only once per source. When astronomers first detected fast radio bursts in the early 2000s, they believed they were witnessing the death throes of massive stars or the violent collisions of exotic objects, scenarios that would naturally produce a burst only once before the source was obliterated or fundamentally altered. Yet observations have revealed that certain sources emit multiple bursts across months and years, suggesting an entirely different mechanism at work. One that can somehow reset itself or exist in a state that permits repeated discharge. The most famous repeating source, discovered in 2015, has produced hundreds of individual bursts, each arriving with patterns that seem almost rhythmic, creating a puzzle that defies conventional astrophysical models because traditional cataclysmic events cannot simply repeat indefinitely without some mechanism to replenish the energy or reconstruct the destroyed material. Scientists have proposed numerous explanations ranging from rapidly rotating neutron stars with unusual magnetic field configurations to hypothetical objects we have no confirmed observations of. Yet none of these theories completely account for the observed characteristics, the precise timing patterns, or the peculiar frequency variations we detect. In the autumn of 2015, an unusual signal emerged from data collected by NASA's Kepler Space Telescope, a mission designed to search for exoplanets by observing the subtle dimming of starlight as celestial bodies pass in front of distant suns. Among thousands of stars being monitored, one particular star designated KIC 8460052, located approximately 1,480 light-years away in the constellation Cygnus, began exhibiting a pattern of brightness fluctuations so anomalous and irregular that it captured the attention of astronomers worldwide and fundamentally challenged conventional understanding of stellar behavior. Star, which would eventually become known as Tabby's star, named after citizen scientist Tabitha Boötes, who led the research team investigating these perplexing variations, displayed dimming episodes unlike anything previously documented in astronomical records, with the star's brightness dropping by up to 22% over the course of just a few days, and then gradually recovering, only to dim again in patterns that seem to defy all established models of stellar physics and behavior. The primary scientific hypothesis attributes this dimming to vast quantities of particulate matter, perhaps fragments of destroyed planets, asteroids, or comet debris arranged in irregular orbits around the star, creating what astronomers describe as an opaque dust veil that periodically obscures our view of the star's surface. Yet this explanation presents profound difficulties, as the mathematical models of planetary dynamics and orbital mechanics struggle to account for how such an enormous concentration of material could remain stable in such close proximity to a star, and how it could produce dimming patterns so utterly irregular and unpredictable that no underlying orbital structure can be reliably discerned. Deep within the cosmic microwave background radiation that fills all of space, astronomers have discovered an enormous region of unusually cold temperature, a vast expanse spanning approximately 1.8 billion light-years across the observable universe, a phenomenon that has come to be known as the cosmic cold spot. When scientists first mapped the temperature variations in the radiation left over from the Big Bang itself, they expected to find a relatively uniform distribution of heat and energy scattered throughout the cosmos in a manner consistent with our current understanding of how the universe expanded and cooled over billions of years. Instead, they found this anomalous zone of extreme cold, a region where temperatures dip significantly below what our models predict they should be, a discrepancy that cannot easily be explained by conventional physics or the standard cosmological framework that has served us so well in other contexts. The discovery emerged from satellite observations conducted over decades, with instruments becoming increasingly sensitive and our maps of the cosmic microwave background growing more detailed and precise, revealing patterns that challenge our deepest assumptions about the universe's structure and uniformity. What makes this phenomenon psychologically compelling is that it represents a direct confrontation between observation and expectation, a moment where the universe refuses to conform to our carefully constructed mathematical models, forcing us to confront the possibility that something fundamental in our understanding may be incomplete or incorrect. Some researchers have proposed explanations suggesting that the cold spot could result from a massive supervoid, an enormous region containing fewer galaxies than average, or perhaps the gravitational influence of structures existing beyond what we can currently observe. Yet these explanations remain speculative and lack the decisive evidence necessary to resolve the mystery completely. In the earliest moments following the Big Bang, when the universe exploded into existence approximately 13.8 billion years ago, the fundamental laws of physics should have created equal quantities of matter and antimatter, two opposing forms of existence that annihilate each other completely upon contact, releasing pure energy in a brilliant flash of light. According to our most rigorous mathematical models and the symmetries we observe in particle physics, there is no reason whatsoever that more matter should have emerged than antimatter in those initial conditions. Yet here we stand, composed entirely of matter, surrounded by galaxies made of matter, existing in a universe dominated overwhelmingly by matter rather than antimatter. This observation presents one of the deepest unsolved mysteries in modern physics, a paradox so fundamental that it challenges our understanding of the universe's most basic operations. The psychological weight of this problem lies in the tension between what our equations predict and what we observe in reality, a gap that suggests something essential is missing from our comprehension of nature's laws. We have discovered through countless experiments that the weak nuclear force, one of the four fundamental forces, does violate a symmetry called CP symmetry under certain circumstances, meaning it does treat matter and antimatter slightly differently. Yet even this violation is far too small to account for the universe's current matter dominance by many orders of magnitude. Scientists have proposed exotic solutions involving hypothetical particles, additional dimensions, or unknown interactions occurring in the first fraction of a second after creation. Yet none of these explanations have achieved widespread acceptance or experimental confirmation. Deep within the cosmos, approximately 250 million light-years away from our position in the Milky Way, there exists a gravitational anomaly of such profound magnitude that it pulls entire galactic clusters toward it with an inexplicable force that defies our conventional understanding of mass distribution and gravitational mechanics. This phenomenon, known as the Great Attractor, was first detected in the 1970s when astronomers noticed that our own galaxy, along with thousands of others, appeared to be moving through space toward a specific region with a velocity that could not be adequately explained by the visible matter we could observe within that region. The gravitational pull exerted by this enigmatic structure is so powerful that it influences the motion of galaxy clusters across hundreds of millions of light years. Yet when researchers point their telescopes toward this location, they find far less visible mass than would be required to generate such an extraordinary gravitational effect. The Great Attractor operates as if it were drawing galaxies toward itself through mechanisms that remain fundamentally mysterious, suggesting that either the region contains vast quantities of dark matter distributed in patterns we do not yet comprehend, or that our models of gravity itself require substantial revision at cosmic scales. What makes this phenomenon psychologically compelling is our tendency to accept the existence of invisible forces that shape the universe without fully acknowledging the profound uncertainty this represents about our foundational understanding of reality itself. We have normalized the Great Attractor into our cosmological framework by simply attributing it to dark matter. Yet this explanation merely replaces one mystery with another, for dark matter remains one of science's most perplexing enigmas. Since the 1990s, a peculiar phenomenon has haunted the trajectory calculations of space agencies worldwide, manifesting itself as a consistent and measurable deviation in the velocities of spacecraft performing gravitational assist maneuvers around Earth, a phenomenon that has become known as the Flyby anomaly, where spacecraft including the Galileo probe, the NEAR spacecraft, the Rosetta mission, and numerous others have all exhibited unexpected changes in their velocities that cannot be adequately explained by the current models of gravitational physics that we rely upon, with some craft experiencing velocity increases while others experience decreases, yet all departing from what the equations of Newton and Einstein would predict with such confidence and precision. The anomalies themselves are remarkably small in magnitude, typically amounting to shifts of mere millimeters per second in the spacecraft's velocity, yet they are consistent enough and repeated enough across multiple independent missions that they cannot be dismissed as mere measurement error or instrumental malfunction, representing instead a genuine discrepancy between observation and theory that persists despite decades of careful investigation and scrutiny. Physicists have proposed numerous hypotheses to account for these deviations, ranging from relativistic effects and electromagnetic interactions with Earth's magnetic field to unaccounted atmospheric drag at high altitudes, and even the influence of exotic matter or modified gravitational principles at work. Yet none of these explanations have achieved universal acceptance or successfully predicted the magnitude and direction of all observed anomalies with consistent accuracy. Deep in the vast cosmic ocean, traveling at tremendous speeds away from our Sun, the Pioneer 10 and Pioneer 11 spacecraft continue their eternal journey through the darkness of space, having been launched in the early 1970s with the primary mission of exploring the outer planets of our solar system. These remarkable machines, which have now traveled for decades beyond their original intended destinations, began exhibiting a peculiar and utterly unexpected gravitational behavior that would puzzle some of the finest physicists in the world for more than 30 years. The anomaly manifested as a subtle but consistent deceleration, a gentle yet persistent slowing that seemed to pull these spacecraft backward with a force that should not exist according to all established laws of physics and our current understanding of gravitational mechanics. Scientists measured this unexpected acceleration with extraordinary precision, determining that both Pioneer spacecraft were being decelerated at a rate of roughly 8.74 multiplied by 10 to the negative 10th meters per second squared, an incredibly tiny amount, but one that was absolutely unmistakable when measured against the silence of space itself. This drift defied explanation because nothing in our theoretical framework could account for it, leading researchers to propose increasingly complex and sometimes desperate theories, including unknown particles in the interstellar medium, uneven heat radiation from the spacecraft's power sources, or perhaps some fundamental flaw in our understanding of gravity at these vast cosmic distances. The psychological mechanism underlying this mystery lies in our deep reliance on the predictability of physical law. Our need to believe that the universe operates according to consistent and knowable rules that we have already discovered or can discover through careful observation and mathematical analysis. Yet here was the universe presenting us with a phenomenon that seemed to operate outside those rules, a small but undeniable whisper suggesting that perhaps our grasp on reality is not as complete as we believed. Deep within the cosmos, astronomers have detected something that should not exist according to our understanding of universal structure, a phenomenon known as the dark flow, which describes a mysterious large-scale motion of galaxy clusters that appears to be streaming toward a particular region of space beyond our observable universe. The discovery emerged from careful analysis of data collected by NASA's Wilkinson Microwave Anisotropy probe, an instrument designed to map the cosmic microwave background radiation that permeates all of space, the ancient light left over from the Big Bang itself. Researchers noticed that galaxy clusters across vast distances were not distributed randomly or moving according to the gravitational pull of visible matter and dark matter as current physics predicts, but instead seemed to be collectively flowing in the same direction, as if drawn by some immense gravitational attractor located beyond the edge of what we can possibly observe. This flow persists across billions of light years, suggesting a coordinated motion influenced by something so extraordinarily massive and so fundamentally distant that its light has not reached us even across the entire age of the universe. The mechanism behind this observation challenges our most fundamental assumptions about cosmic structure, because standard gravitational theory cannot account for such organized motion without invoking either unknown matter of unimaginable proportions or reconsidering whether our models of universal expansion and large-scale geometry are incomplete in ways we have not yet considered. Scientists have proposed various explanations, including the existence of a supermassive attractor located beyond the cosmic horizon, or alternatively, that we inhabit a region of space that is itself moving through an even larger structure we cannot yet perceive. In the vast expanse of the universe, roughly 1 billion light-years away from Earth, there exists a region of space so profoundly empty that it has earned a haunting designation among cosmologists: the Boötes void, a spherical region spanning approximately 250 million light-years in diameter containing virtually no galaxies whatsoever. This immense bubble of nothingness sits within the constellation Boötes and represents one of the largest cosmic voids ever discovered, a space so devoid of matter that astronomers have struggled to reconcile its existence with our fundamental understanding of how the universe should be structured and distributed. The void was first identified in the late 1980s when researchers mapping galaxy distributions noticed an enormous spherical region in which the expected density of galaxies simply did not appear, leaving behind only the faintest traces of dark matter and a perplexing emptiness that stretches the imagination to contemplate. What makes the Boötes void particularly anomalous is that according to conventional models of cosmic structure formation, the universe should have evolved with a relatively uniform distribution of matter on large scales, with density variations forming galaxies, clusters, and superclusters in a somewhat predictable pattern. The void's existence suggests either that our models of structure formation are fundamentally incomplete, or that processes we do not yet understand have conspired to create this region of profound emptiness. Astronomers theorize that such voids may have formed through the migration of dark matter and baryonic matter away from the region, leaving behind a space where gravity has failed to accumulate sufficient material to birth new galaxies. Yet the precise mechanisms driving such wholesale evacuation remain deeply mysterious and contested within the scientific community. Deep within the cosmos lies a measurement problem so fundamental that it threatens to unravel our entire understanding of the universe's expansion, a contradiction that cosmologists have come to call the Hubble tension crisis. This tension arises from a seemingly simple question: how fast is the universe actually expanding? Yet the answer depends critically on how we measure it and therein lies the crisis. When astronomers observe distant supernovae and measure their redshift and distance using standard candles, they calculate that the universe is expanding at approximately 73 kilometers per second per megaparsec. However, when physicists examine the cosmic microwave background radiation left over from the Big Bang itself and extrapolate forward using our best theoretical models of the early universe, their calculations suggest an expansion rate of approximately 67 kilometers per second per megaparsec. The discrepancy may seem minor in purely numerical terms, but in the context of fundamental physics, this gap represents a genuine crisis of understanding that cannot be easily dismissed or explained away. The psychological mechanism underlying our continued acceptance of this contradiction involves a peculiar form of scientific compartmentalization, wherein we maintain two competing frameworks simultaneously without fully integrating their implications. We have become accustomed to operating within what might be called a state of productive uncertainty, where our minds are trained to hold contradictory measurements as equally valid within their respective domains, trusting that future discoveries will eventually reconcile the two approaches. Yet decades have passed since this tension first became apparent, and instead of resolving, the measurements have only grown more precise and more stubborn in their refusal to agree, suggesting that perhaps something fundamental in our theoretical architecture requires reconstruction rather than mere adjustment. Deep within the cosmic furnace of the early universe, during those first few minutes after the Big Bang, nuclear fusion created the lightest elements in existence, and among them was lithium, a metal so rare and precious that its abundance tells us something fundamental about the nature of reality itself. Astronomers and physicists have spent decades measuring the amount of lithium present in the oldest stars we can observe, particularly in ancient globular clusters, where these stellar relics have remained virtually unchanged since the dawn of time, and they have consistently found that the universe contains far less lithium than our most sophisticated theoretical models predict it should contain. According to Big Bang nucleosynthesis theory, which describes how the first atomic nuclei formed in the blazing heat of the primordial cosmos, there should be approximately 3 times more lithium-7 floating throughout space than what we actually observe when we point our telescopes at the heavens and analyze the light signatures of these ancient suns. This discrepancy, known as the cosmological lithium problem, represents a profound gap between what our equations tell us should exist and what nature has chosen to reveal to us through direct observation. The mechanism behind this puzzle lies in the fundamental way we model the early universe and the nuclear reactions that occurred within the first minutes of existence. When physicists calculate how protons and neutrons combine to form helium, deuterium, and lithium in the superheated plasma of the primordial epoch, they rely on well-established nuclear cross-sections and reaction rates that have been measured and verified countless times in terrestrial laboratories and particle accelerators. Yet somehow, when these calculations are extrapolated back to cosmic scales and compared with actual observations of stellar compositions, a stubborn inconsistency emerges that refuses to be easily reconciled. One of the most profound mysteries confronting modern cosmology is the discovery that the cosmic microwave background, the ancient light left over from the Big Bang itself, is not distributed evenly across the entire sky as our fundamental understanding of the universe suggests it should be. Instead, when astronomers carefully map the temperature fluctuations of this primordial radiation in extraordinary detail, they found that one hemisphere of the observable universe appears systematically warmer than the other, a phenomenon known as hemispherical asymmetry. This asymmetry manifests as a dipole pattern where radiation appears slightly hotter when looking in one particular direction through space and correspondingly cooler in the opposite direction, a finding that contradicts the cosmological principle, which posits that the universe should appear roughly the same in all directions when viewed on sufficiently large scales. The temperature difference itself is minute, amounting to only a few microkelvin, yet the statistical significance of this imbalance is profound, suggesting something fundamentally irregular about either the structure of the cosmos or our position within it. The psychological impact of this discovery operates on multiple levels within the scientific community, for it challenges the assumption of cosmic democracy, the comforting notion that humanity occupies no special vantage point in the universe and that isotropy prevails on the grandest scales. Researchers have proposed numerous theoretical explanations, ranging from the influence of unknown massive structures beyond the observable universe to exotic forms of physics that operate at the very edge of spacetime itself, yet none have achieved consensus or complete explanatory power. The asymmetry persists in our data despite decades of increasingly sophisticated observations, and rather than disappearing as instrumental errors or statistical anomalies, it remains robust across multiple independent measurements and datasets. In the early 2000s, cosmologists studying the cosmic microwave background radiation, the ancient light left over from the Big Bang itself, discovered something profoundly unsettling within their data. When they examined the temperature fluctuations across the entire observable universe, they found that these fluctuations were not randomly distributed as modern physics predicted they should be, but instead appeared to align along a specific axis stretching across the cosmos. This alignment became known as the axis of evil, a name chosen partly in jest, but carrying genuine scientific concern about what such an alignment might mean for our understanding of universal structure. The temperature variations, the very seeds from which galaxies and stars would eventually form, seem to prefer one particular direction through space, as though the universe itself possessed an inherent orientation or preferred geometry that should not exist according to our most fundamental theories. Multiple independent research teams verified this anomaly, confirming that the alignment was far too precise and far too pronounced to be dismissed as mere statistical noise or observational error. The mechanism behind this preference for direction remains deeply mysterious, as the cosmological principle, one of the foundational assumptions underlying modern physics, explicitly states that the universe should look essentially the same in all directions from any vantage point. There is no logical framework within current theoretical physics that adequately explains why such an axis should exist at all, yet here it persists in the observational record, visible to anyone who knows how to read the ancient light surrounding us. When astronomers began measuring the rotational speeds of galaxies in the mid-20th century, they discovered something that should have fundamentally shaken our understanding of the cosmos, yet somehow it settled into our collective consciousness as merely another unsolved puzzle rather than a crisis of knowledge. Galaxies, those vast islands of billions of stars, were rotating in a manner that contradicted everything we understood about gravity and mass distribution based on our most reliable mathematical frameworks. According to classical mechanics and general relativity, the stars at the outer edges of a galaxy should move more slowly than those near the center, much like planets in our solar system move more slowly the farther they are from the sun. This prediction follows logically from the observed mass concentrated at galactic centers and the gravitational laws we have tested and verified countless times. Yet when scientists pointed their telescopes and instruments toward spiral galaxies and measured their actual rotation rates, they found something profoundly strange. The outer regions of galaxies rotated nearly as fast as the inner regions, maintaining velocities that should have been impossible given the visible mass present. The rotation curves, when plotted on graphs, remained stubbornly flat rather than declining as physics suggested they should. To reconcile this discrepancy between observation and theory, the scientific community proposed the existence of dark matter, an invisible substance that comprises the vast majority of galactic mass, yet interacts with light not at all. This solution, while mathematically elegant, essentially transformed an observational problem into an invisible one, replacing the mystery of incorrect rotation curves with the deeper mystery of what comprises 85% of the matter in galaxies. Despite decades of searching for direct evidence of dark matter particles, despite increasingly sensitive experiments and theoretically motivated candidates, no definitive detection has been achieved. Deep within the cosmos, something fundamental appears to be vanishing without a trace, and despite decades of intensive observation and theoretical refinement, physicists remain unable to account for approximately half of all the ordinary matter that should exist in the universe. The missing baryon problem, also known as the baryon accounting crisis, represents one of the most perplexing discrepancies in modern astrophysics, where our best calculations and observations refuse to reconcile with one another in any satisfactory way. When astronomers measure the density of baryonic matter, the ordinary atoms and particles that comprise stars, planets, galaxies, and everything we can directly observe, they find that the universe contains only about half the amount of baryons that the Big Bang nucleosynthesis model predicts should be present based on the radiation signatures and fossil evidence left over from the earliest moments of cosmic creation. This is not a minor computational error or small gap between theory and observation, but rather a profound absence of approximately 50% of the material that fundamental physics insists must exist. The psychological impact of this discrepancy operates on multiple levels within the scientific community, as it challenges the foundational assumptions about the universe's composition and our ability to observe and measure the cosmos accurately. Scientists have proposed various explanations ranging from baryons hiding in hot intergalactic gases and diffuse clouds of matter distributed throughout space, to the possibility that our understanding of the Big Bang itself requires fundamental revision. Some researchers suggest that the missing baryons exist in the form of warm-hot intergalactic medium, an extremely rarefied plasma distributed across the vast spaces between galaxy clusters, which would be extraordinarily difficult to detect with conventional astronomical instruments. High above and below the galactic center of our Milky Way, two colossal structures extend outward like cosmic balloons, each stretching approximately 25,000 light-years into the darkness of space, and these formations, known as the Fermi bubbles, represent one of the most perplexing mysteries in modern astrophysics because despite decades of observation and study, scientists remain fundamentally uncertain about what mechanism could have created such enormous structures with such apparent symmetry and power. Discovered in 2010 through gamma-ray observations from the Fermi Gamma-Ray Space Telescope, these bubbles were found to be regions of heightened energy emission, suggesting that some extraordinarily violent event or process must have occurred at the galactic center to propel material and energy outward in such a dramatic fashion. The primary challenge in understanding the Fermi bubbles lies in the sheer magnitude of energy that would be required to inflate structures of this scale. And while astronomers have proposed several theories ranging from past accretion disk activity around the supermassive black hole Sagittarius A star to jets launched from active galactic nuclei, or even the accumulated effect of multiple stellar explosions occurring in concert. None of these explanations adequately accounts for all the observed characteristics of the bubbles, including their perfect symmetry, their distinct boundaries, and the specific distribution of energy across them. We find ourselves in the peculiar position of having mapped these structures in detail and measured their properties with considerable precision. Yet the fundamental question of their origin remains beyond our current theoretical framework, and this gap between observation and explanation has become normalized within the scientific community in a way that allows continued research to proceed without the pressure of immediate resolution. Deep within the cosmic fabric of our universe exists a phenomenon that continues to perplex astrophysicists and theoretical physicists worldwide. The arrival of ultra-high-energy cosmic rays that strike Earth's atmosphere with such tremendous force that their origins remain fundamentally unexplained, and their existence seemingly violates the established constraints of modern physics itself. These are not ordinary particles. They are subatomic projectiles traveling at speeds so close to that of light that their kinetic energy exceeds anything we can reliably produce in our most powerful particle accelerators, yet they originate from sources we cannot definitively identify or locate. The most remarkable aspect of this mystery involves what scientists call the GZK cutoff, a theoretical limit suggesting that cosmic rays traveling across vast intergalactic distances should lose energy when interacting with the cosmic microwave background radiation that permeates all of space. Yet observatories around the world continue to detect rays arriving with energies far exceeding this supposed threshold. As though some unknown acceleration mechanism in the depths of space operates beyond our current understanding of physics. When these ultra-high-energy rays collide with Earth's upper atmosphere, they create spectacular cascades of secondary particles called cosmic ray showers that rain down through layers of air in events so powerful they release energy equivalent to a professional baseball traveling at highway speeds, striking a single molecule. The human mind tends to compartmentalize such impossibilities, treating them as exotic curiosities rather than fundamental challenges to our most cherished theories about how the universe operates. We have developed elaborate frameworks to explain away these anomalies through speculative mechanisms like neutron star collisions, supermassive black hole jets, or exotic particle decay. Yet none of these proposed sources adequately accounts for the frequency, energy levels, and directional distribution of the rays we observe with increasing clarity every year. In the depths of space, where distant galaxies spin silently through the cosmic void, our most sophisticated detection instruments have begun recording something deeply troubling, an abundance of gamma rays that our current models of physics cannot adequately explain. This phenomenon, known as the gamma ray excess, represents a persistent mystery that challenges our understanding of stellar processes, particle physics, and the fundamental nature of matter itself. Observations from space-based telescopes, particularly the Fermi Gamma Ray Space Telescope and ground-based observatories, have detected gamma-ray emissions coming from regions of space where our mathematical models predict far fewer photons should exist, and this discrepancy has grown increasingly difficult to dismiss as mere instrumental error or statistical anomaly. The gamma rays arrive at Earth carrying energy far beyond what conventional astrophysical processes should produce, suggesting that either our understanding of how stars, black holes, and supernovae generate radiation is fundamentally incomplete, or that some entirely unknown process is at work in the cosmos. Scientists initially proposed dark matter annihilation as an explanation, theorizing that when dark matter particles collide in certain regions of space, they produce gamma rays as a byproduct. Yet subsequent calculations and observations have rendered this explanation increasingly implausible without introducing new theoretical particles that themselves lack independent verification. The mystery deepens further when we consider that the excess gamma rays often originate from the galactic center and other locations where dark matter is theoretically most concentrated. Yet the magnitude of the excess far exceeds what current dark matter models predict, creating a troubling gap between expectation and observation. Deep within the cosmos exist some of the most extreme objects ever theorized by modern astrophysics, and among them are magnetars, neutron stars so extraordinarily dense and magnetized that they challenge our fundamental understanding of matter and energy themselves. Magnetar is born from the catastrophic collapse of a massive star, compressing more mass than our entire sun into a sphere no larger than a city, creating a gravitational environment so severe that a teaspoon of magnetar material would weigh as much as all the mountains on Earth combined. What makes magnetars truly remarkable, however, is their incomprehensibly powerful magnetic fields, which can reach strengths of 10 to the 15th Gauss, compared to Earth's magnetic field of merely half a Gauss. Occasionally, these magnetars experience what astronomers call starquakes, sudden catastrophic ruptures in their crusts that release more energy in a single second than our sun has emitted over an entire year. Yet we struggle to explain how this is physically possible. When a magnetar starquake occurs, it generates gamma-ray bursts of such intensity that they could theoretically disrupt the magnetospheres of planets in neighboring star systems. Yet these events continue to happen in ways that seem to violate the energy conservation principles we believe should govern the universe. The magnetic field itself may be twisting violently during these ruptures, reorganizing its vast energy in patterns we cannot fully predict or model, and the stress accumulated in the magnetar's crust releases suddenly in a way that appears almost instantaneous from our perspective. We have normalized this phenomenon by simply observing it, cataloging the events, and accepting that magnetars exist in a regime where extreme physics operates according to rules we have yet to fully comprehend. Yet we rarely pause to consider how such events might reshape our assumptions about what is theoretically possible in the universe. Deep within the cosmos, astronomers have discovered something that shouldn't exist according to our most carefully constructed theories of stellar physics, a region of impossible silence in the universe where no objects appear to occupy a particular range of masses between neutron stars and black holes. When massive stars reach the end of their lives and collapse under their own gravity, they leave behind either a neutron star, those incredibly dense remnants where a teaspoon of material would weigh as much as a mountain on Earth, or they collapse further into black holes, those regions of spacetime from which nothing can escape, not even light itself. Yet between these two distinct categories lies a mysterious void, a mass gap where gravitational collapse should produce objects, but observational evidence suggests that almost nothing exists in this intermediate range, defying our understanding of how stellar death must necessarily progress. Astronomers have observed numerous neutron stars ranging up to about 2 or 3 times the mass of our Sun, and they have detected black holes ranging downward to about 5 times the mass of our Sun. But this leaves a perplexing emptiness between approximately 3 and 5 solar masses where physics insists objects should form, yet our telescopes find almost nothing there. The theoretical framework that governs how matter behaves under extreme pressure and density cannot easily explain why nature would skip over this particular range, as if some invisible hand prevents matter from settling into this forbidden zone. Perhaps these objects do exist but remain hidden from our current detection methods, or perhaps the physics governing the transition between stellar remnant types operates in ways we have not yet comprehended, suggesting that our equations are incomplete or that we misunderstand the fundamental processes occurring in the final moments of stellar collapse, leaving us to contemplate an empty region in the universe that persistently refuses to conform to our predictions about how reality should organize itself. When a massive star collapses at the end of its life, it forms one of the universe's most extreme objects, a black hole, a region of spacetime so densely compressed that not even light can escape from beyond its event horizon. For decades, physicists have grappled with a profound mystery that emerges from combining two of our most successful theories of physics, a mystery that suggests something fundamental about reality itself may be incomplete or wrong. Stephen Hawking discovered in 1974 that black holes are not entirely black, but rather emit radiation due to quantum effects near the event horizon, and this radiation carries energy away, causing the black hole to gradually evaporate and disappear from the universe. The paradox arises from a troubling implication of this process. If a black hole evaporates completely, all the information about the matter and energy that fell into it would be permanently lost from the universe, violating a core principle of quantum mechanics which states that information cannot be destroyed, only transformed or hidden. This creates a logical contradiction at the very heart of theoretical physics, forcing us to question whether quantum mechanics, general relativity, or perhaps both theories require fundamental revision. The psychological weight of this paradox lies in its challenge to our deepest assumptions about causality and information conservation. Physicists have spent generations developing frameworks where the past can always theoretically be recovered from the present, yet black holes seem to offer a loophole, a mechanism by which the universe could genuinely forget. Despite the profound nature of this contradiction, the scientific community has largely normalized the ongoing debate, cycling through proposed solutions like information scrambling, holographic principles, and soft hair theorems, each attempting to preserve either quantum mechanics or our intuitions about information without truly resolving the fundamental tension. Deep within the mathematical framework of general relativity lies a peculiar and troubling phenomenon that has confounded theoretical physicists for nearly a century, a phenomenon we call the singularity, that point of infinite density where all known laws of physics collapse entirely and cease to function in any meaningful way. At the heart of every black hole, contemporary models suggest, there exists a region of spacetime so warped, so fundamentally broken, that our most reliable equations simply produce infinity as an answer, which is not truly an answer at all, but rather a confession of mathematical failure disguised as a scientific prediction. What is particularly anomalous about this situation is that we have constructed an entire theoretical edifice, complete with tensor equations and sophisticated mathematical machinery, to describe something that explicitly cannot be described by those very same tools, creating what might be called a self-refuting framework of understanding that persists regardless. The human mind possesses a remarkable capacity to inhabit contradictions when they are sufficiently abstract and sufficiently distant from everyday experience, allowing us to discuss singularities with scientific authority while simultaneously acknowledging that they represent the boundary where science itself becomes incoherent and unreliable. We have normalized the existence of these mathematical dead zones, these regions where our physics breaks down completely, treating them as interesting puzzles rather than as fundamental indictments of our theoretical models, perhaps because the alternative, admitting that our most successful scientific theories are incomplete and possibly fundamentally flawed, would require rebuilding our understanding of gravity and spacetime from the ground up. In 1974, Stephen Hawking proposed one of the most elegant and troubling theories in modern physics, that black holes are not entirely black, but rather emit a faint radiation due to quantum effects occurring at the event horizon, a phenomenon that would later bear his name and fundamentally challenge our understanding of thermodynamics and the ultimate fate of the universe. According to this theoretical framework, particle-antiparticle pairs spontaneously materialize in the quantum foam near the event horizon, and when one particle falls into the black hole while the other escapes, the escaping particle carries away energy that was extracted from the black hole's mass itself, causing it to slowly evaporate over astronomical timescales. This radiation represents a bridge between quantum mechanics and general relativity, two pillars of physics that rarely coexist peacefully, and it suggests that black holes possess a temperature and entropy proportional to their surface area rather than their volume, inverting everything we thought we knew about thermodynamic laws. Yet despite being mathematically rigorous and supported by decades of theoretical work, Hawking radiation has never been directly detected, not once, in all the years since its proposal. No observatory has captured the signature of this evaporating radiation from any black hole in our universe, and this absence persists despite the fact that astronomers have identified numerous black holes of varying masses and proximity to Earth, from stellar mass remnants to supermassive monsters at the centers of galaxies. The challenge lies partly in the weakness of the effect. For stellar mass black holes, the radiation would be extraordinarily faint and drowned out by the far brighter radiation from infalling matter, while for supermassive black holes, the radiation would be so negligible that detection becomes practically impossible with current technology. Deep within the mathematical framework of general relativity lies a theoretical twin to one of the universe's most profound mysteries, a concept born not from observation, but from the elegant symmetry of Einstein's equations themselves. White holes represent a hypothetical time-reversed version of black holes, regions of spacetime where matter and energy would theoretically only flow outward rather than inward, creating a one-way membrane through which nothing could ever enter, but from which everything continuously emerges. The mathematics that predicts their existence is rigorous and compelling, derived from the same equations that have accurately described gravitational phenomena for more than a century. Yet not a single white hole has ever been definitively observed in our universe, and therein lies the profound puzzle. When physicists first solved the Schwarzschild equations in general relativity, they discovered that the mathematics permitted both an inward-pointing singularity, which we recognize as a black hole, and an outward-pointing singularity, which the theory termed a white hole, suggesting a perfect duality in the fabric of spacetime itself. The theoretical mechanism underlying white holes involves time-reversal symmetry, the principle that the laws of physics should operate identically whether time flows forward or backward, yet our observable universe appears fundamentally asymmetrical in this regard. The psychological appeal of white hole theory rests on our deep human need for cosmic symmetry and balance, the intuition that if nature creates destructive voids that consume everything, there should exist corresponding fountains that create and distribute matter outward. Yet despite decades of advanced astronomical observation and the construction of increasingly sensitive instruments capable of detecting gravitational waves and electromagnetic radiation from the most violent cosmic events, we have never found evidence of a white hole's existence. Deep within the vast emptiness of space, high-energy particles known as cosmic rays bombard Earth's atmosphere constantly from all directions, yet observations reveal something profoundly inexplicable. These particles do not arrive uniformly from across the celestial sphere, but instead demonstrate a distinct directional bias, a preference for certain regions of the sky that modern physics cannot adequately explain. Scientists have measured this cosmic ray anisotropy with increasingly sophisticated instruments, detecting that the highest energy cosmic rays appear to arrive more frequently from specific directions in the cosmos, particularly from regions near the galactic plane and toward the constellation Cygnus. Yet the sources and mechanisms that would create such a pronounced directional preference remain deeply mysterious and resistant to conventional theoretical frameworks. The anisotropy becomes even more puzzling when considering that these cosmic rays travel across incomprehensible distances through the galaxy, passing through magnetic fields that should scatter and randomize their trajectories, making their apparent ordering and directional preference seem like a statistical impossibility that defies our understanding of how charged particles behave over cosmic scales. What makes this phenomenon particularly unsettling is the human tendency to compartmentalize it as merely another unexplained feature rather than a fundamental challenge to our models, treating it as background noise in the greater symphony of cosmic mysteries rather than recognizing it as evidence that something essential about particle physics or the structure of space itself may elude our current comprehension. When physicists first developed the mathematics of antimatter in the early 20th century, they discovered something profoundly symmetrical in the equations of particle physics. For every particle of ordinary matter, there should exist a corresponding particle of antimatter with identical mass but opposite electrical charge. According to these elegant mathematical formulations, the Big Bang should have created equal quantities of matter and antimatter, which would have immediately annihilated each other in a catastrophic explosion of pure energy, leaving behind nothing but radiation and an empty universe. Yet here we are, surrounded by galaxies, stars, planets, and life itself, composed entirely of ordinary matter. This fundamental asymmetry remains one of the deepest mysteries in physics, known as the Baryon asymmetry problem, and it becomes even more perplexing when we consider what we do not observe in the cosmos. Despite decades of sophisticated astronomical surveys, sensitive particle detectors, and advanced telescopic observations, we have never identified a single antimatter galaxy anywhere in the observable universe. We see no regions of space where antimatter predominates, no distant clusters composed of antiprotons and positrons, no evidence of the vast quantities of antimatter that the universe's creation should have produced. The absence is so complete, so total, that it demands explanation yet resists it. Our current physics can describe what happens when matter and antimatter meet, can calculate the precise energy released, can predict the gamma-ray signatures that such collisions should produce. Yet we cannot adequately explain why antimatter appears to have vanished almost entirely from our cosmos, or why the universe fundamentally favors matter over its mirror opposite. This absence haunts the theoretical framework we have constructed, sitting quietly at the edge of our understanding like an unanswered question that grows more profound with each passing year. When physicists calculate the energy density of empty space itself, they arrive at a number so staggeringly large that it defies comprehension. A prediction suggesting that the vacuum of the universe should possess an energy density approximately 120 orders of magnitude greater than what we actually observe in our cosmos. This discrepancy, known as the vacuum catastrophe problem or the cosmological constant problem, represents one of the most profound and unsettling failures in theoretical physics, a gap so enormous that it makes all other scientific inconsistencies appear trivial by comparison. According to quantum field theory, empty space is not truly empty at all, but rather seethes with virtual particles constantly appearing and disappearing in a ceaseless dance of creation and annihilation, each fluctuation contributing to the overall energy of the void. And when physicists attempt to sum these contributions across all possible frequencies and all possible particles, the total energy density they calculate is so fantastically immense that it should have torn the universe apart in the first fraction of a second after the Big Bang, collapsing it back into nothingness instantaneously. Yet our universe did not collapse. It expanded then, and it continues to expand now, suggesting that either our understanding of quantum mechanics is fundamentally wrong, or our understanding of gravity is fundamentally wrong, or both, or that some unknown mechanism of extraordinary precision exists to cancel out this catastrophic vacuum energy with almost supernatural exactitude. The psychological mechanism underlying how we have normalized this absurdity is rooted in compartmentalization and institutional acceptance, where physicists have learned to simply acknowledge the problem while continuing to work within existing frameworks, treating the discrepancy as a puzzle to be solved rather than an indictment of the entire theoretical edifice upon which modern physics rests. Deep within the theoretical framework of modern physics lies a prediction so fundamental, so mathematically elegant, that physicists have spent decades searching for evidence of its occurrence, yet what they have found instead is a profound and unsettling silence. The proton, that building block of all atomic nuclei, was predicted by many unified field theories to be unstable, to gradually decay into lighter particles over incomprehensibly vast timescales measured in billions of years. And yet, despite constructing some of the most sensitive detection equipment ever created, scientists have never observed a single proton undergoing this predicted decay. The theoretical calculations suggested that in a large body of matter containing approximately 10 to the 32nd power protons, we should witness roughly one decay event per year, a prediction that led researchers to construct enormous underground chambers filled with ultrapure water or other materials, shielded from cosmic rays, equipped with photomultiplier tubes capable of detecting the faintest whisper of light that would result from a proton's final transformation. The logic behind this search remains sound even as the empirical results contradict it, because many grand unified theories that elegantly bind together the fundamental forces of nature almost require proton decay to occur as a necessary consequence of their mathematical structure. Yet the proton refuses to decay, at least not in any measurable way, and this absence has persisted for decades as experiments have grown increasingly sophisticated and sensitive. The psychological mechanism at work here involves what might be called inverted expectation, where the absence of a phenomenon becomes itself anomalous because the mathematics that describe our universe suggested it should be present. And this creates a peculiar cognitive dissonance where we have trained ourselves to accept that our most elegant theoretical predictions might be fundamentally incomplete or flawed. Deep within the realm of particle physics, where the rules governing our universe are written in mathematics and verified through countless experiments, there exists a measurement so fundamental that it should be among the most well-established facts in all of science. Yet the proton, that tiny positively charged particle at the heart of every hydrogen atom and a core component of all matter, remains stubbornly resistant to giving us a definitive answer about its size. For decades, physicists measured the proton's radius using one particular method, arriving at a value that seemed consistent and reliable through multiple experimental approaches. However, in 2010, a new technique employing muonic hydrogen, which is an exotic atom composed of a proton and a muon rather than an electron, produced a startlingly different result. The muonic hydrogen measurements indicated that the proton is approximately 4% smaller than all previous estimates had suggested, a discrepancy that might sound trivial until one recognizes that this challenges fundamental assumptions embedded deep within quantum electrodynamics, one of the most precisely validated theories in human history. The puzzle deepens when considering that this inconsistency suggests something is fundamentally wrong either with our understanding of how particles interact, or with the measurements themselves, yet attempts to resolve the contradiction have only generated further confusion and spawned an entire cottage industry of theoretical speculation. Physicists have proposed exotic particles, modifications to established equations, and systematic errors in apparatus design, yet the proton steadfastly refuses to resolve the ambiguity. What makes this anomaly particularly unsettling is that the proton appears to behave differently depending on what we use to measure it, almost as though it possesses an intrinsic knowledge of our investigative methods and responds accordingly. Deep within the precision laboratories where physicists probe the fundamental nature of matter itself, an anomaly persists that has quietly troubled the standard model of particle physics for decades, a discrepancy so small yet so persistently measurable that it refuses to be dismissed as mere experimental error. The muon, an elementary particle that bears a striking resemblance to the electron but carries approximately 207 times its mass, possesses a magnetic moment, a property that describes how strongly it interacts with magnetic fields. And when scientists measure this magnetic moment with extraordinary precision, using techniques involving particle rings and detector systems of breathtaking complexity, they discover that the muon's behavior deviates from what the standard model predicts with a consistency that has now accumulated across multiple independent experiments conducted over several decades. This anomaly, known as muon G-2, represents a gap between theoretical prediction and experimental observation that, while measured in parts per million, cannot be easily explained away by known physics, suggesting either that our understanding of quantum electrodynamics requires revision or that previously unknown particles and forces might be exerting subtle influences on this particular particle's properties. The psychological mechanism that allows this discrepancy to persist without immediate resolution lies in the inherent conservatism of scientific practice itself, where anomalies of this magnitude are treated not as immediate invalidations of existing frameworks, but rather as hints pointing toward deeper layers of reality waiting to be discovered. Yet the very precision required to measure this effect and the extraordinary technical challenges involved in conducting these experiments mean that the muon magnetic anomaly remains confined to the world of specialized particle physics laboratories and theoretical papers, known only to specialists and enthusiasts, rather than entering the public consciousness as a fundamental crisis in our understanding of nature. Among the most elusive particles in the universe, neutrinos present one of physics' most stubborn unsolved problems. We still do not know their actual mass, despite decades of sophisticated experimentation and theoretical refinement. These ghostly particles, produced in abundance by the Sun, by supernovae, and by the Big Bang itself, pass through our bodies and the entire planet in countless trillions every single second. Yet they interact so weakly with ordinary matter that detecting them requires massive underground detectors filled with thousands of tons of specially purified liquid or sensitive crystalline arrays. The standard model of particle physics, which has proven remarkably accurate in describing the fundamental forces and particles of nature, initially predicted that neutrinos should be massless, a prediction that aligned perfectly with observations for many decades. However, in the late 1990s and early 2000s, experiments measuring neutrino oscillations, a phenomenon where neutrinos change from one type to another as they travel through space, revealed something astonishing. This transformation could only occur if neutrinos possessed mass, contradicting the established theoretical framework. The profound implication was that something fundamental about our understanding of particle physics required revision, yet the precise mass values remained frustratingly beyond our grasp, hidden beneath experimental uncertainty and instrumental limitations. We know neutrinos must be remarkably light, billions of times lighter than electrons, yet we cannot determine their exact masses or even establish a definitive ordering of the three known types, a hierarchy that would itself illuminate deep principles of nature. This mystery has persisted because the detection of neutrino mass differences requires extraordinary precision, and despite construction of ever more sensitive experiments across multiple continents, the margin of error remains stubbornly large relative to the signal we seek. The Sun's outer atmosphere, known as the corona, presents one of the most perplexing mysteries in solar physics, a phenomenon that has troubled astronomers and physicists for nearly 2 centuries. When scientists observe the Sun using specialized instruments and spectroscopic analysis, they discover that the photosphere, which is the visible surface of the Sun, maintains a temperature of approximately 5,800 Kelvin. Yet paradoxically, the corona that extends outward from this surface reaches temperatures exceeding 1 million Kelvin, sometimes climbing as high as 3 million Kelvin in certain regions. This represents an inversion of every thermal principle we understand about heat transfer and energy dissipation. Heat should radiate away from a source, diminishing as distance increases, much like how the warmth from a fire weakens the further away you stand from it. The corona, however, defies this fundamental expectation by becoming dramatically hotter the further it extends from the Sun's heat source, as though some invisible mechanism were continuously pumping enormous amounts of energy into the outer atmosphere rather than allowing it to cool naturally. Scientists have proposed numerous theories attempting to explain this counterintuitive observation, including wave heating mechanisms where magnetic waves dissipate their energy in the corona, reconnection events where magnetic field lines suddenly snap and release stored energy, and particle acceleration processes involving complex interactions between charged particles and magnetic structures. Despite decades of dedicated research, satellite observations, and advanced computational modeling, none of these proposed mechanisms has achieved complete validation or full acceptance within the scientific community. The paradox persists in our understanding of solar physics, remaining one of the most fundamental unresolved questions about how our nearest star actually functions. Deep within the chromosphere of our Sun lies one of the most perplexing mysteries in modern astrophysics, a phenomenon so counterintuitive that it has confounded scientists for over 7 decades. The Sun's corona, that ethereal halo of plasma visible during total solar eclipses, exists at temperatures exceeding 2 million degrees Kelvin, yet the photosphere beneath it, the visible surface we observe, maintains a comparatively modest temperature of merely 6,000 degrees. By all conventional understanding of thermodynamics and heat transfer, this arrangement should be impossible. Heat should flow from the hot photosphere upward into the cooler corona, not the other way around, yet somehow the corona burns with an intensity that defies logical expectation. Since its discovery in the 1920s, physicists have grappled with this inversion, proposing countless mechanisms to explain how energy reaches such tremendous heights. Magnetic field reconnection, acoustic wave dissipation, and particle acceleration theories have all been advanced, yet none satisfactorily accounts for the magnitude of heating observed. The human mind, when confronted with such apparent reversals of natural law, often defaults to acceptance through familiarity, transforming the inexplicable into the mundane through repeated exposure. We have named the problem, quantified it, assembled arrays of satellites to measure it, and in doing so, we have somehow convinced ourselves that understanding the terminology constitutes genuine comprehension. The coronal heating problem persists in scientific literature, attracting research funding and brilliant minds, yet it remains stubbornly unresolved, a testament to the limits of our current theoretical frameworks and the profound mysteries that continue to inhabit the very star that makes life on Earth possible. Deep in the geological record, approximately 4.5 billion years ago, our sun was considerably dimmer than it is today, shining with only about 70% of its current luminosity. Yet somehow during this period of reduced stellar output, evidence suggests that the early Earth maintained liquid water on its surface and possessed conditions suitable for the emergence of life itself. A contradiction so profound that it has puzzled planetary scientists and astrophysicists for decades and continues to challenge our fundamental understanding of stellar evolution and planetary habitability. The physics of stellar nucleosynthesis tells us with remarkable certainty that as stars age and accumulate helium in their cores through the fusion of hydrogen, their internal pressure and temperature increase, causing them to gradually brighten over time in a predictable and mathematically describable process. Yet when we examine the Archean and Proterozoic eons through geological proxies such as paleosol chemistry, isotopic ratios in ancient rocks, and the fossil record of microbial life, we discover unambiguous signs that Earth's oceans were liquid, that weather systems moved across the surface, and that organisms thrived in these waters, all of which requires substantial atmospheric warming and a habitable climate that seems physically impossible given the reduced solar output of that era. The mechanism underlying this paradox appears rooted in how we construct models of planetary habitability and stellar evolution, for we assume that the relationship between solar luminosity and planetary climate must follow strict physical laws that leave no room for alternative energy sources or feedback mechanisms. Yet when we examine early Earth's atmospheric composition through chemical models and geological evidence, we find tantalizing hints of significantly elevated concentrations of methane, carbon dioxide, and other greenhouse gases that could have compensated for the dimmer sun, creating a warm climate through an intensified greenhouse effect that modern atmospheric models suggest was theoretically possible, though difficult to sustain. In September of 2020, an international team of astronomers announced the detection of phosphine gas in the atmosphere of Venus, a discovery that sent ripples through the scientific community and captured the imagination of those seeking signs of extraterrestrial life. The signal was detected using radio observations from the James Clerk Maxwell Telescope in Hawaii, and subsequently confirmed through data from the Atacama Large Millimeter Array in Chile, revealing what appeared to be measurable concentrations of phosphine, a compound that on Earth is primarily associated with biological processes and the metabolism of certain anaerobic microorganisms. The researchers suggested that while phosphine could theoretically be produced through non-biological chemical processes on Venus, the quantities detected seemed difficult to explain through conventional atmospheric chemistry alone, prompting cautious speculation about the possibility of microbial life existing in the cooler, more hospitable cloud layers of our neighboring world. However, this announcement became almost immediately controversial, as subsequent analyses and peer reviews raised significant questions about the data processing methodologies, the reliability of the initial measurements, and whether the detected signal could indeed be explained through known geological and chemical processes rather than biological ones. The scientific debate that followed highlighted a peculiar aspect of human reasoning. We are drawn to explanations that satisfy our emotional desires to find life beyond Earth, sometimes allowing that attraction to influence our interpretation of ambiguous data, even when we possess the rational capacity to recognize such bias in ourselves. This tendency became particularly evident in how rapidly the initial phosphine findings were disseminated through popular media, often stripped of their preliminary and speculative nature, before the scientific community had adequately assessed their validity. Since the Mars Science Laboratory rover began its extended mission across the Martian surface in 2012, instruments designed to detect and measure atmospheric composition have recorded something deeply perplexing: sudden, dramatic spikes in methane concentrations that appear and disappear with no discernible pattern or explanation. These methane surges have been observed multiple times over the years, with atmospheric methane levels rising from a baseline of roughly 600 parts per billion to peaks exceeding 1900 parts per billion, before dropping back down again in what seems like a seasonal or perhaps entirely random cycle. The methane itself presents a fundamental puzzle because on Earth, methane is typically produced by biological processes, by decomposition and microbial activity, yet Mars is believed to be largely sterile, a cold and inhospitable world where such organic processes should not occur. The planet's thin atmosphere and harsh radiation environment seem entirely incompatible with the kind of biochemical activity that generates methane on our world, and yet the measurements persist, recorded by multiple independent instruments and verified by different methods of detection. The scientific community has proposed various geological explanations, suggesting that perhaps subsurface water interactions with certain minerals might produce methane through purely chemical means, or that ancient reservoirs of the gas trapped deep beneath the Martian crust occasionally release their contents through geological fracturing or hydrothermal activity. Yet none of these explanations fully account for the temporal distribution of the spikes, for their seemingly episodic nature, for the way they appear to concentrate around certain regions and then vanish entirely. Deep within the thick, orange atmosphere of Saturn's moon Titan lies a mystery that continues to perplex planetary scientists and atmospheric chemists alike. For the methane that swirls through this distant world's clouds and rains down upon its hydrocarbon lakes appears to be vanishing far more rapidly than any known geological process could possibly replenish it. The Cassini spacecraft, during its remarkable 13-year mission orbiting Saturn, detected substantial quantities of methane distributed throughout Titan's atmosphere. Yet when scientists calculated the rate at which ultraviolet radiation from the distant sun breaks apart these methane molecules through a process known as photodissociation, they discovered an alarming discrepancy that has resisted conventional explanation. The mathematics are straightforward and appear incontrovertible. The methane in Titan's atmosphere should have been completely depleted, converted entirely into more complex organic compounds, and lost to space within a time frame of merely 10 to 20 million years, which is far shorter than the 4.5 billion year age of our solar system itself. Yet Titan continues to possess a substantial methane atmosphere, suggesting that some unknown source must be continuously replenishing this volatile compound at rates that would need to rival the loss mechanisms to maintain the observed atmospheric composition. Scientists have proposed that cryovolcanism, the eruption of water and ammonia slurries from beneath Titan's icy crust, might serve as a methane source, though direct observational evidence of such activity remains elusive and inconsistent with our current models of how such processes should function at Titan's frigid surface temperatures of negative 319 degrees Fahrenheit. Enceladus, one of Saturn's smallest moons, presents a thermal puzzle that continues to perplex planetary scientists and astrophysicists who study our solar system's hidden mysteries. This ice-covered moon, no larger than the state of Arizona, emanates approximately 5 to 10 times more heat energy than current gravitational models can adequately explain through tidal friction alone, the primary mechanism by which we understand how orbital bodies generate internal warmth. The Cassini spacecraft, during its extended mission through the Saturnian system, detected remarkable plumes of water vapor and organic compounds erupting from hydrothermal vents near Enceladus's south polar region, plumes that suggest an active subsurface ocean maintained by this inexplicable surplus of thermal energy. When scientists calculate the expected heat production from tidal dissipation, accounting for the moon's orbital eccentricity and its gravitational interactions with Saturn and neighboring moons, the mathematics consistently fall short of what observations reveal. The conventional explanation of tidal heating relies on the deformation and friction within a rocky body's interior. Yet Enceladus appears far too small and insufficiently positioned within Saturn's gravitational field to generate such prodigious amounts of heat through this process alone. The discrepancy has led researchers to propose various mechanisms, exotic internal structures, unusual mineral compositions, or perhaps gravitational resonances we have not yet fully characterized, yet none have achieved complete consensus or fully resolved the paradox. What remains particularly striking is how the scientific community has adopted a kind of measured acceptance regarding this anomaly, treating it as simply another mystery awaiting future data rather than a fundamental challenge to our models of planetary mechanics. As though the accumulation of unexplained phenomena gradually normalizes the extraordinary until it becomes merely another data point requiring patient investigation and eventual reconciliation with existing theory. Deep within the vast expanse of our solar system, Jupiter radiates into the cold vacuum of space, an extraordinary amount of thermal energy that continues to perplex and humble our most rigorous calculations and observational models. The gas giant, composed primarily of hydrogen and helium, emits approximately twice as much energy as it receives from the distant sun, a phenomenon that has been documented through infrared measurements and thermal imaging for decades, yet remains fundamentally unexplained within the conventional framework of planetary physics and stellar thermodynamics. This surplus energy radiates outward in all directions, heating the planet's atmosphere to temperatures far exceeding what solar radiation alone could possibly generate, creating atmospheric patterns and storm systems of incomprehensible scale and persistence. Scientists have proposed various theoretical mechanisms to account for this anomaly, including the hypothesis that Jupiter possesses residual heat from its formation billions of years ago, a primordial warmth that has somehow resisted the inevitable entropy and cooling that physics suggests should have occurred across such vast periods of time. Yet this explanation remains unsatisfying and incomplete when subjected to rigorous mathematical scrutiny and thermal modeling. The mechanism behind this persistent energy generation could theoretically involve unknown processes occurring within Jupiter's dense core, perhaps gravitational compression or exotic forms of matter undergoing reactions we do not yet comprehend. Yet we have normalized the existence of this anomaly into our standard planetary science curricula without ever truly resolving its fundamental contradiction with our understanding of energy conservation and thermodynamic principles. Deep within the upper atmosphere of Saturn, a geometric impossibility rotates with undeniable persistence, a massive hexagonal storm system that has confounded planetary scientists since its discovery in the 1980s, and continues to challenge our fundamental understanding of atmospheric dynamics and fluid mechanics, even as our most advanced instruments observe it in meticulous detail. This hexagon, spanning approximately 14,000 miles across at its widest points, maintains its perfectly symmetrical six-sided geometry while rotating at velocities exceeding 1,000 miles per hour, with winds that spiral inward toward a central vortex of such intensity that the entire structure appears as though it were designed by some cosmic architect, rather than emerging from the chaotic interplay of planetary rotation and atmospheric pressure differentials. The storm has persisted for decades without deterioration, defying all conventional models of how weather systems should behave, as meteorologists have long understood that such geometric precision should be impossible in fluid systems, where turbulence and entropic forces typically dissolve organized structures into formless chaos within relatively short timescales. The mechanism that produces this hexagon remains deeply mysterious, as laboratory simulations and mathematical models have suggested that rotating fluid dynamics could theoretically produce such shapes under very specific conditions. Yet the fact that Saturn maintains this exact configuration year after year suggests something far more mysterious at work, something that preserves geometric order against the overwhelming entropy that should gradually obliterate it. Deep within the Jovian system orbits one of the solar system's most volcanically active bodies, a moon called Io, which presents scientists with a persistent puzzle regarding the sheer intensity and consistency of its volcanic output. Io's surface is dominated by hundreds of active volcanoes, some of which erupt with such tremendous force that their plumes extend hundreds of kilometers into the thin atmosphere. Yet what makes this particularly anomalous is that the heating mechanism responsible for this activity appears to generate far more energy than the models predict should be possible. The tidal heating theory explains that Io's volcanism results from friction generated by Jupiter's immense gravitational pull, which flexes the Moon's interior as it orbits in an elliptical path alongside its sister moons Europa and Ganymede, creating internal stress and heat. However, the observed heat output from Io's volcanoes consistently exceeds what calculations based on tidal friction alone can account for, suggesting either that our understanding of how tidal forces dissipate energy is incomplete, or that some additional, unknown heating mechanism operates within this distant world. Scientists have observed that Io's volcanic activity shows patterns of seeming regularity interrupted by sudden surges in intensity that don't correlate neatly with the Moon's orbital mechanics, and the composition of the eruptions themselves varies in ways that challenge existing geochemical models. Despite decades of observation and increasingly sophisticated theoretical frameworks, the exact proportions of heat generated by tidal friction versus heat generated by internal radioactive decay versus any other potential energy source remain uncertain and contested. The phenomenon persists as a fundamental mystery partly because we have normalized the idea that orbital mechanics should be sufficient to explain Io's behavior. Yet the data consistently suggests something more complex operates in the darkness of that distant moon, something that continues to defy our expectations and assumptions about how planetary bodies should behave. Our moon presents one of the most perplexing formation puzzles in planetary science, a celestial object whose origins seem to contradict several fundamental principles of how we believe our solar system assembled itself billions of years ago. According to the dominant giant impact hypothesis, our moon formed approximately 4.5 billion years ago when a Mars-sized planetary body, often referred to as Theia, collided catastrophically with the early Earth in what would have been an extraordinarily violent cosmic collision. This impact supposedly ejected enormous quantities of material from both the Earth and this impacting body into orbit, and from this debris field, our moon gradually coalesced through gravitational accretion into the celestial companion we observe today. Yet when scientists examine the details of this mechanism with rigorous mathematical modeling and physical analysis, numerous inconsistencies emerge that challenge the viability of this widely accepted explanation. The moon's orbital characteristics, its unusual density composition compared to Earth, the isotopic ratios found in lunar samples, and the angular momentum distribution of the Earth-Moon system all present statistical improbabilities that the giant impact hypothesis struggles to satisfactorily resolve. Many alternative formation scenarios have been proposed over decades of research, including fission theories, capture hypotheses, and various collision models with different impact parameters. Yet none have achieved complete consensus or fully explained every anomalous observation. What becomes psychologically compelling about this situation is how the scientific community has essentially settled upon the impact hypothesis as the default explanation despite its unresolved problems, transforming it from a tentative working model into something approaching established fact in public discourse and educational curricula. For centuries, astronomers and lunar observers have documented fleeting, unexplained luminous events dancing across the surface of the moon, phenomena that appear without warning, persist for mere moments or hours, and then vanish entirely as if they never existed at all. These events, collectively known as lunar transient phenomena or LTP, manifest as sudden brightenings, colorful glows, localized fog-like obscurations, and mysterious flashes of light concentrated primarily around certain geological features such as crater rims, mountain peaks, and regions near tectonic boundaries. Yet they remain stubbornly resistant to any comprehensive scientific explanation, despite decades of observation and technological advancement. Reputable astronomers from institutions worldwide have documented thousands of these incidents with increasing precision over the past 3 centuries, with sightings becoming notably more frequent during periods of heightened solar activity and lunar seismic events, suggesting some connection to energy sources we do not fully understand. And yet each event continues to baffle researchers because the moon, being geologically dead with no substantial atmosphere, possessed no obvious mechanism that could produce such visible disturbances or luminous displays under conventional physics. The psychological mechanism driving our acceptance of these phenomena may stem from our tendency to compartmentalize observations that do not fit established models, treating them as measurement errors or optical illusions rather than genuine physical events worthy of complete investigation and fundamental reconsideration of our lunar models. We have become comfortable relegating these thousands of documented sightings to the realm of curiosity rather than crisis, assigning them names like transient phenomena as if nomenclature itself provides explanation. And by doing so, we have effectively normalized the existence of a major celestial mystery that occurs regularly above our heads and demands answers we have yet been unable to provide with confidence or consensus among the scientific community at large. Deep within the outer reaches of our solar system, beyond the orbit of Neptune, where sunlight becomes merely a distant pinprick in the absolute darkness of space, astronomers have detected gravitational anomalies that cannot be easily explained by the objects we know to exist in that region. Beginning around 2016, researchers studying the trajectories and orbital patterns of distant icy bodies known as transneptunian objects noticed something peculiar. These small worlds seemed to be clustered and influenced in ways that suggested the presence of an unseen massive body, a potential ninth planet orbiting in the cosmic deep, a world we have never directly observed despite its presumed size and influence. The mathematical models indicated this hypothetical planet would be substantially larger than Earth, perhaps 10 times more massive, moving through an elongated orbit that takes it incredibly far from our Sun, spending most of its existence in regions of space so distant that our telescopes cannot yet reliably detect it. What makes this phenomenon particularly fascinating is how it persists as a genuine mystery despite our advanced technological capabilities, for we possess the mathematical sophistication to infer the presence of something we cannot see, yet we lack the observational tools to confirm it with absolute certainty. The psychological mechanism that sustains our fascination with Planet 9 relates to our deep human need to complete patterns and to fill voids in our understanding, a compulsion that dates back to our earliest astronomical observations when ancient cultures connected stars into constellations to make sense of chaos. We recognize gravitational signatures, we analyze orbital irregularities, we run simulations demonstrating that known objects alone cannot account for what we observe, and yet the object itself remains elusive, unrevealed, refusing to surrender itself to our instruments, maintaining a profound mystery at the very edge of our cosmic neighborhood. Deep within the outer reaches of our solar system, beyond the orbit of Neptune, lies a region known as the Kuiper Belt, a vast reservoir of icy bodies and dwarf planets that scientists have long theorized should extend gradually outward in decreasing density. Yet when astronomers began mapping this distant region with increasing precision, they discovered something that fundamentally challenged their models of solar system formation. A dramatic and unexplained edge, a sharp boundary where the population of objects suddenly and dramatically drops off, as though an invisible wall had been erected to mark the outer limit of planetary construction. This phenomenon, known as the Kuiper Cliff, represents one of the most puzzling structural features in our cosmic neighborhood, defying conventional understanding of how planetary systems naturally develop and organize themselves over billions of years. The psychological mechanism behind our acceptance of the Kuiper Cliff lies in our tendency to compartmentalize mysteries within specialized domains, allowing them to persist in scientific literature without generating widespread concern or demanding immediate resolution. We have constructed elaborate theoretical frameworks, invoking gravitational interactions with passing stars, the migration of Neptune during the early solar system's chaotic period, or collisional cascades that systematically cleared the outer regions. Yet none of these explanations fully accounts for the cliff's sudden and precise nature. Our minds find comfort in the existence of plausible mechanisms, even when those mechanisms remain unproven and incomplete, and we have normalized the Kuiper Cliff as simply another feature awaiting better instruments and further study, rather than recognizing it as a profound gap in our understanding of how planetary systems actually form. At the edge of our solar system, far beyond the orbit of Neptune and the Kuiper Belt's icy bodies, astronomers propose the existence of a vast spherical shell of icy objects known as the Oort cloud, a theoretical region that may contain billions or even trillions of comets and small celestial bodies orbiting the Sun at distances measured in light-years rather than astronomical units. Despite decades of advanced telescopic observation, sophisticated detection equipment, and the considerable resources dedicated to understanding our cosmic neighborhood, not a single direct observation of the Oumuamua cloud has ever been made, nor has any object confirmed to originate specifically from this proposed region been photographed or analyzed in real time. The cloud remains entirely inferred through mathematical models and indirect evidence, constructed from comet trajectories and orbital calculations that suggest such a distant reservoir of objects must exist to explain the periodic return of long-period comets that occasionally venture toward the inner solar system. This represents a peculiar phenomenon in modern astronomy where an enormous and supposedly fundamental structure of our solar system remains perpetually beyond the reach of human observation, existing primarily as a conceptual placeholder in our understanding of celestial mechanics. The human mind demonstrates a remarkable capacity to accept as established fact the existence of objects and regions that have never been directly observed, provided that the logical framework supporting their existence appears mathematically consistent and fills an explanatory gap in existing theories. We construct elaborate models and diagrams depicting the Oumuamua cloud as though we have mapped it thoroughly, yet the cloud persists as a ghost in our scientific literature, a necessity conjured to resolve inconsistencies between prediction and observation rather than a confirmed reality. Deep within the cosmos, astronomers have observed something that should not be possible according to our current understanding of how the universe is structured and distributed, and this phenomenon involves the mysterious alignment of quasars across vast distances of space that appear to follow patterns far too organized to be the result of random cosmic chance. When researchers began mapping the positions and orientations of these incredibly distant and luminous objects, they discovered that quasars seem to align along preferred axes and directions in ways that suggested an underlying order to the universe on the largest scales imaginable, almost as though invisible threads connected them across billions of light years. The sheer improbability of such arrangements occurring by accident alone has led astronomers to question whether some unknown force or principle might be organizing these objects. Yet no mechanism has been convincingly identified to explain how such vast cosmic structures could coordinate their positions and orientations across distances so enormous that light itself takes billions of years to traverse them. The human mind tends to seek patterns in all things, finding meaning and connection even in randomness, and this psychological tendency sometimes leads us to interpret genuine data through the lens of order and design, causing us to wonder whether we are discovering true cosmic principles or merely seeing what our brains are predisposed to see in complicated datasets. In the vast mathematical landscape of theoretical physics, cosmic strings represent one of the most peculiar and persistent anomalies in our attempts to understand the fundamental structure of the universe itself. These hypothetical one-dimensional topological defects are predicted to exist as remnants from the earliest moments following the Big Bang, when the universe underwent rapid cooling and symmetry breaking in ways that our current observational instruments have never directly confirmed. Unlike ordinary matter or energy, cosmic strings would theoretically be infinitely thin, yet possess tremendous mass density, stretching across billions of light years while remaining completely invisible to our most sensitive telescopes and detection equipment. The theory emerged from quantum field theory in the 1970s as physicists grappled with fundamental problems in particle physics and cosmology. Yet despite decades of intensive research and mathematical refinement, not a single cosmic string has ever been observed or definitively detected, despite numerous predictions about their gravitational signatures and potential electromagnetic emissions. What makes this anomaly particularly fascinating is how thoroughly the scientific community continues to invest intellectual and financial resources into searching for evidence of something that may not exist at all, treating the absence of detection not as definitive proof of absence, but rather as an indication that our search methods remain inadequate or that cosmic strings exist at densities far below current theoretical predictions. The psychological mechanism sustaining this pursuit appears rooted in the remarkable explanatory power that cosmic string theory provides for otherwise intractable problems in physics, particularly regarding the formation of large-scale cosmic structures, galaxy formation, and the apparent distribution of matter throughout the observable universe. Deep within the fabric of spacetime itself, cosmologists have detected something that shouldn't exist according to our most refined understanding of gravitational physics. A persistent hum of gravitational waves that permeates the entire observable universe, a background radiation of warped spacetime that appears far more powerful and prevalent than current models can adequately explain. When we listen to the data collected by the Laser Interferometer Gravitational Wave Observatory and the Virgo detector, we encounter gravitational waves arriving from all directions simultaneously, creating what scientists call the stochastic gravitational wave background, a phenomenon that represents one of the deepest mysteries in modern astrophysics. According to Einstein's general relativity, gravitational waves should only be produced by violent cosmic events, colliding neutron stars, merging black holes, the explosive deaths of massive stars. Yet the sheer intensity and omnidirectional nature of this background suggests sources we have not yet identified or understood. Our current models predict that known sources like binary black hole mergers and neutron star collisions should generate only a faint whisper of gravitational radiation when combined, yet the detectors consistently register signals that appear to exceed these calculated predictions by orders of magnitude. The human mind responds to this incomprehensibility by compartmentalizing it into the category of unknown sources, assigning phantom origins like primordial black holes or hypothetical cosmic strings to account for the excess energy. Yet these explanations themselves remain untested and largely speculative. We have normalized this profound gap between observation and theory by treating the gravitational wave background as merely another puzzle awaiting future technological advancement, rather than confronting the possibility that our fundamental understanding of how gravity operates across cosmic scales may require substantial revision. Deep within the solar corona, astronomers have detected a persistent and troubling discrepancy that challenges our fundamental understanding of stellar physics and energy production. The Sun, that ancient furnace at the center of our solar system, appears to be producing fewer photons than our most rigorous calculations predict it should be generating based on the observable mass conversion occurring within its core. When we measure the actual photon flux arriving at Earth and work backwards through the mathematics of nuclear fusion, accounting for every known absorption mechanism and scattering process throughout the intervening space, we find ourselves facing a significant deficit, a ghost of missing light that refuses to be adequately explained by conventional solar models. This phenomenon, termed the photon underproduction crisis by researchers who study it, suggests that either our models of stellar nucleosynthesis are fundamentally incomplete, or that some mechanism of light absorption or transformation exists within the Sun's structure that we have yet to identify or properly account for. The psychological and conceptual mechanism that allows this anomaly to persist in the scientific literature, without more urgent investigation, stems from our tendency to assume that minor discrepancies will eventually resolve themselves as instruments improve and measurements become more precise. We have normalized this gap between prediction and observation by categorizing it as a calibration issue or a measurement uncertainty, rather than confronting the possibility that it might represent a genuine limitation in our theoretical framework. Scientists continue their work within the existing paradigm, hoping that better data will simply confirm what we already believe to be true, creating a self-perpetuating cycle where the anomaly becomes merely background noise in an otherwise functioning model. Yet the numbers persist, the deficit remains measurable and reproducible, and somewhere in that space between what we expect and what we observe lies a truth that awaits our willingness to truly listen. Deep within the universe's distant past, astronomers have discovered massive clouds of hydrogen gas that emit an intense ultraviolet glow, particularly within the Lyman alpha wavelength, and these structures have been named Lyman alpha blobs, mysterious objects that challenge our conventional understanding of how galaxies form and evolve across cosmic time. These enormous nebulous structures, some stretching across hundreds of thousands of light years, represent some of the largest and most luminous objects known to exist in the early universe. Yet their power source and formation mechanism remain profoundly unclear despite decades of intensive observation and theoretical analysis. The phenomenon was first identified when space-based telescopes detected regions of abnormally bright hydrogen emission at such vast distances that the light has been traveling toward us for billions of years, allowing us to observe them as they appeared in the universe's infancy. What makes Lyman alpha blobs particularly perplexing is that their observed luminosity appears to exceed what standard astrophysical models predict should be possible, suggesting either unknown energy generation mechanisms at work within these systems or fundamental gaps in our understanding of early cosmic processes. The prevailing explanations propose that either heavily obscured supermassive black holes lurk within these structures, or multiple young galaxies clustered together produce the observed emissions, or perhaps shockwaves from galactic collisions energize the surrounding hydrogen gas into this distinctive fluorescence. Yet when astronomers examine these objects more carefully with advanced spectroscopy and multi-wavelength imaging, the data consistently refuses to align perfectly with any single proposed mechanism, instead indicating that Lyman alpha blobs may operate through processes we have not yet properly identified or theorized. In the constellation Eridanus, which flows across the southern celestial hemisphere like an invisible river of stars, astronomers have discovered something that should not exist according to our current understanding of cosmic structure. A region of space so profoundly empty that it defies conventional cosmological models and challenges the very foundations of how we believe the universe to be distributed. This vast expanse, known as the Eridanus supervoid, stretches across billions of light years and contains roughly 1,000 times fewer galaxies than we would statistically expect to find in a volume of space this immense, creating a gravitational anomaly that ripples through our comprehension of large-scale universal geometry. The void was first identified through careful analysis of cosmic microwave background radiation patterns and galaxy distribution surveys, revealing a cold spot in the sky that corresponds to a region where matter itself seems to have been evacuated or never accumulated in the first place. What makes this phenomenon particularly vexing to modern physics is that the prevailing lambda-cold dark matter model, which has successfully explained so much about cosmic structure and evolution, offers no satisfactory mechanism for creating such dramatic underdensities on these scales, suggesting either that our gravitational models require fundamental revision or that we are observing the aftermath of cosmic processes we have yet to adequately theorize. The psychological mechanism that allows this anomaly to persist in relative obscurity despite its profound implications stems from our tendency to compartmentalize observations that contradict our preferred models rather than allow them to trigger wholesale theoretical reconstruction, as well as from the genuine difficulty in observing and confirming such vast empty spaces where the absence of light and matter makes verification inherently challenging. Deep within the constellation Cygnus, approximately 1,400 light-years from Earth, exists a star catalogued as KIC 8462852, which has captivated astronomers with a pattern of dimming so irregular and profound that it defies conventional stellar physics. The star exhibits unpredictable dips in brightness, sometimes fading by up to 20%, and these fluctuations follow no discernible pattern that our current models can adequately explain. Traditional stellar phenomena like planetary transits produce regular, repeating dips with mathematical precision, yet KIC 846252 dims sporadically, as though something massive and structurally chaotic orbits within its system, occluding its light in ways that seem almost deliberately inconsistent. Scientists initially proposed the existence of a dense cluster of fragments, perhaps the remnants of a shattered planetary system or the debris field surrounding a catastrophic collision. Yet even this explanation strains against the observational data when one considers the sheer scale and irregularity of what telescopes have recorded. The human mind seeks pattern and predictability in the cosmos, finding comfort in mathematical relationships and repeating cycles that allow us to believe we understand the universe's fundamental operations. When confronted with KIC 846252, this deeply embedded psychological need for order encounters something that resists categorization, something that orbits beyond our frameworks of understanding. We have developed elaborate theoretical models to normalize the anomaly, assigning it properties and compositions that maintain our sense of cosmic coherence, yet the star continues to dim according to rules we have not yet grasped. Despite decades of observation and analysis, despite the application of sophisticated telescopes and computational models, KIC 846252 persists in its irregular dimming, almost as though indifferent to our attempts at comprehension. Deep in the southern skies, approximately 600 light-years away, exists a star known as HD 10160555, more commonly referred to as Przybylski's star, named after the astronomer who first documented its peculiar spectroscopic properties in 1961. What makes this distant stellar body so profoundly mysterious is the presence of extraordinarily rare elements within its atmosphere that should not exist in such concentrations according to our current understanding of stellar nucleosynthesis and cosmic chemistry. The star's spectrum reveals alarming abundances of holmium, thulium, and other lanthanides, those exotic elements found only in the deepest reaches of the periodic table, elements that are typically created only during the most violent cosmic events. Yet here they appear in ratios that seem impossible given the star's apparent age and composition. Scientists have observed that these rare Earth elements exist in proportions that cannot be easily explained by standard theories of how stars generate and distribute chemical elements throughout their lifespans. The psychological mechanism at work here involves our deep human need to categorize and understand the universe through predictable physical laws, and when we encounter something that contradicts those fundamental assumptions, we experience a cognitive dissonance that compels further investigation. We construct elaborate hypothetical mechanisms to explain the anomaly, whether through exotic stellar phenomena, the remains of destroyed planetary bodies, or unusual convection patterns that might concentrate rare elements in ways we have not yet observed elsewhere. Yet despite decades of study, despite the application of increasingly sophisticated spectroscopic instruments and computational models, Przybylski's star continues to resist definitive explanation, maintaining its enigmatic quality as a celestial object that operates according to rules we do not yet comprehend, reminding us that the universe remains fundamentally willing to surprise those who seek to understand it. Deep within the observational records of modern cosmology exists a peculiar discrepancy that has come to be known as the sigma-8 tension, a statistical anomaly that emerges when astronomers compare measurements of cosmic structure gathered through different observational methods across our universe. When scientists observe the large-scale distribution of matter through gravitational lensing, the way light bends around massive structures, they arrive at specific values for how clumped and clustered the universe's material has become over billions of years. Yet when those same researchers examine the cosmic microwave background radiation, the ancient light left over from the Big Bang itself, and then project forward what the current state of cosmic clustering should be according to our best models, they consistently arrive at slightly different numbers. The tension between these two measurement approaches has grown increasingly significant over the past decade, with the discrepancy now standing at several standard deviations, a threshold that in physics typically suggests something fundamental may be wrong with our understanding. The sigma-8 value itself represents a normalized measure of matter fluctuation density, essentially describing the amplitude of cosmic structures on scales of roughly 100 million light-years. What makes this anomaly so intellectually unsettling is that both measurement methods are independently sound, both are performed by competent researchers using well-calibrated instruments, and yet they persistently refuse to align with one another. This persistent disagreement could indicate that our models of how gravity operates on cosmological scales may require revision, or that dark energy behaves differently than we currently theorize, or perhaps that entirely new physics beyond our standard framework plays an unexpected role in cosmic structure formation. Deep within the cosmic web that stretches across billions of light-years, astronomers have observed a phenomenon so peculiar and so mathematically improbable that it challenges our fundamental understanding of how galaxies form and evolve throughout the universe. When researchers began cataloging the rotational axes of distant galaxies, they expected to find a random distribution, with each galaxy spinning in its own independent direction relative to our cosmic vantage point, much like spinning tops scattered randomly across an infinite floor. However, what they discovered instead was that galaxies within certain clusters and along filamentary structures appear to possess a statistical preference for aligning their spin axes in particular orientations, as though some invisible cosmic choreographer had gently arranged them in subtle synchronization. This alignment is subtle enough that it goes unnoticed by casual observation, yet precise enough that statistical analysis reveals a deviation from pure randomness that cannot easily be dismissed as mere coincidence. The mechanism behind this phenomenon remains deeply puzzling to cosmologists because current gravitational models and the prevailing theories of galaxy formation through hierarchical merging cannot adequately explain how such large-scale correlations could persist across such enormous distances of space. One might expect that the gravitational interactions during galactic collisions and mergers would scramble any initial alignments, creating complete randomness, yet instead we observe this mysterious tendency toward preferred orientations. The human mind struggles to accept that the universe operates with hidden symmetries and organizational principles that transcend our conventional understanding of gravitational physics. And so astronomers have developed increasingly complex mathematical frameworks attempting to explain this alignment without fundamentally reconsidering whether our models of cosmic structure formation might be incomplete or missing essential components. When astronomers peer back toward the beginning of time itself using our most powerful telescopes, they encounter a profound and unsettling mystery that challenges the fundamental timeline upon which all modern cosmology rests. According to our current understanding of the universe, the cosmos began approximately 13.8 billion years ago, and in those first chaotic moments after the Big Bang, matter was distributed relatively uniformly throughout space, gradually clumping together under gravity to form the first stars and galaxies. Yet observations from the James Webb Space Telescope and other deep-field imaging instruments have revealed the existence of fully formed, massive galaxies existing when the universe was only a few 100 million years old, far too early according to our models for such complex structures to have possibly assembled. These ancient galaxies appear to possess the same level of maturity and structural sophistication as galaxies we observe today, suggesting that the gravitational processes required to forge them together would have required billions of years rather than merely hundreds of millions. The psychological mechanism underlying how we maintain our composure in the face of this paradox operates through a peculiar form of scientific accommodation, wherein we have quietly accepted that our models might require adjustment without fundamentally questioning whether our foundational assumptions about cosmic history deserve deeper scrutiny. We have essentially normalized the impossible by transforming it into a puzzle awaiting a solution rather than a sign that something more fundamental about our understanding requires revision. Astronomers continue their work, proposing increasingly elaborate mechanisms by which gravity might work faster in the early universe or suggesting exotic forms of dark matter that could accelerate galaxy formation. Yet these remain speculative patches applied to a foundational timeline that may itself be flawed. Deep within the observational archives of modern astronomy lies one of the most perplexing contradictions yet discovered, a galaxy so distant and so ancient that its very existence challenges our understanding of cosmic evolution and the fundamental physics that governs light and matter across the universe. The galaxy designated GNZ11 was observed in the infrared spectrum by the Hubble Space Telescope and represents one of the most distant objects ever detected, situated approximately 13.4 billion light-years away from Earth, which means we are observing it as it existed merely 400 million years after the Big Bang itself. Yet here emerges the profound paradox that has troubled astrophysicists since its discovery. This galaxy appears far too luminous, far too mature, and far too structurally complex for such an impossibly early epoch in cosmic history. According to our current models of galaxy formation and evolution, structures of this magnitude and brightness should not have been able to assemble themselves in so short a time frame, as the universe simply would not have had sufficient duration for the necessary processes of stellar birth, accumulation of matter, and structural organization to occur naturally within the accepted framework of physics and cosmology. The luminosity problem persists because GNZ11 shines with a brightness that suggests it contains stellar populations, and mass far exceeding what calculations predict should be possible at such an early cosmic epoch. Scientists have proposed various explanations, including the possibility of modified initial mass functions in early galaxies, extraordinarily efficient star formation rates, or the influence of supermassive black holes driving unusual accretion processes, yet none of these theoretical adjustments fully resolve the observational contradiction. The galaxy continues to exist in our data, undeniably real and undeniably bright, while the models that should explain it remain incomplete, leaving us in the peculiar position of accepting a phenomenon whose existence we cannot yet adequately explain through established physical principles. In the earliest moments following the Big Bang, the universe existed in a state of profound darkness, filled with neutral hydrogen atoms that absorbed and scattered light indiscriminately, creating an impenetrable fog across all of creation. Around 380,000 years after the initial expansion, the universe cooled sufficiently for electrons and protons to combine into neutral atoms, an event known as recombination, which paradoxically made space even more opaque to radiation. Yet somewhere between roughly 150 million and 1 billion years after the Big Bang, something extraordinary occurred. The entire universe underwent a dramatic transformation called reionization, during which neutral hydrogen was stripped back into its ionized state, allowing light to travel freely once more and illuminating the cosmos with the first stars and galaxies. The mystery that continues to perplex modern astrophysics is how this reionization happened so quickly and so completely, as if an invisible hand had switched on every light simultaneously across incomprehensible distances. Our current models suggest that early galaxies and quasars produced ultraviolet radiation energetic enough to ionize hydrogen, yet the calculations consistently reveal a fundamental problem. There simply should not have been enough ionizing sources present during the observed timeline to accomplish what actually occurred, creating what astronomers call the photon budget crisis. The puzzle deepens when we consider observations from the James Webb Space Telescope and other instruments, which have detected fully formed galaxies existing during the reionization epoch, structures so massive and mature that they could not have had time to develop through conventional theories of galaxy formation and evolution. Despite decades of refinement to our models, despite supercomputer simulations and increasingly sophisticated observational data, the reionization epoch remains fundamentally inconsistent with our understanding of how structures form and how radiation propagates through space. In the vast cosmic catalog of astronomical discoveries that have emerged over the past 2 decades, few observations have proven as perplexing and fundamentally troubling to our understanding of galactic structure as the detection of what astronomers now call dark matter-free galaxies, vast collections of stars and stellar material that appear to contain little to no dark matter whatsoever. A finding that directly contradicts one of modern physics' most foundational assumptions about how galaxies must be constructed and held together. These galaxies, first identified through careful observational studies beginning in the early 21st century, present a scenario that should not theoretically exist according to our current models of gravitational dynamics and galactic formation. Yet they persist in the observable universe with an almost stubborn indifference to our expectations. The primary mechanism by which these galaxies confound our understanding rests in the simple fact that we have constructed an elaborate theoretical framework in which dark matter serves as the gravitational glue holding galaxies together, the invisible scaffolding upon which visible matter arranges itself. And without sufficient dark matter present, these structures should either fly apart due to insufficient gravitational cohesion or never have formed in the first place. What we observe instead are fully formed, stable galaxies rotating with velocities consistent with their visible mass alone, suggesting that either our understanding of gravity itself requires fundamental revision, or dark matter distribution is far more variable and unpredictable than contemporary cosmological models have suggested. In the vast catalog of cosmic structures that populate our universe, there exists a class of galaxies so peculiar and so fundamentally challenging to our understanding of how galaxies should form and function that astronomers have only recently begun to systematically study them in earnest. These are the ultra-diffuse galaxies, or UDGs, as they are commonly abbreviated in astronomical literature, and they represent one of the most vexing anomalies in our current models of galactic formation and evolution. An ultra-diffuse galaxy is defined as a galaxy that possesses a stellar mass comparable to that of the Milky Way, or even larger, yet spreads this enormous quantity of stars across a volume of space so vast and so dilute that the galaxy becomes virtually invisible to conventional observation, appearing as little more than a ghostly whisper against the darkness of space. What makes this phenomenon so deeply troubling to physicists and astronomers is the simple mathematical reality that such galaxies should not exist according to our most fundamental theories about how gravity operates on cosmic scales. When we apply the equations of gravitational dynamics to a system with such a low stellar density, the mathematics tells us that the stars should have long ago dispersed into the intergalactic void, pulled apart by tidal forces and scattered across billions of light years. Yet there they remain, held together in some manner that our current models cannot adequately explain, suggesting that either our understanding of gravity itself requires modification, or that these galaxies contain vast quantities of matter that remains entirely invisible to us. The prevailing hypothesis suggests that ultra-diffuse galaxies are held together by enormous halos of dark matter, far more massive and more extensive than the dark matter we believe surrounds ordinary galaxies. Yet this explanation itself raises profound questions about the nature of dark matter and how its distribution comes to be so dramatically different in these systems compared to all others. In the depths of space, stretching across nearly 10 billion light-years of cosmic distance, exists a structure so monumentally vast that it challenges not only our understanding of the universe's architecture, but also the very foundations of modern cosmological theory. The Hercules-Corona borealis Great Wall, discovered through meticulous examination of gamma-ray burst distributions and subsequent observational confirmation, represents a collection of galaxy clusters and superclusters arranged in a wall-like configuration that defies conventional explanations of how such immense structures could have formed within the accepted timeline of cosmic evolution. The structure spans approximately 10 billion light-years across, making it one of the largest known objects in existence, yet its presence contradicts the assumptions we have built regarding the universe's homogeneity and the mechanisms responsible for large-scale structure formation. When cosmologists observe such titanic arrangements of matter, they encounter a profound disconnect between theoretical predictions and observational reality, because current models suggest that the universe simply has not existed long enough to permit gravitational forces to assemble matter into formations of this magnitude and scale. The psychological mechanism underlying our continued acceptance of this anomaly involves a form of intellectual compartmentalization, wherein we acknowledge the structure's existence while simultaneously maintaining our attachment to cosmological models that cannot adequately explain its formation or stability. We have adopted the practice of cataloging these structures, measuring them with increasing precision, and publishing peer-reviewed analyses of their properties, yet we rarely confront the uncomfortable reality that their existence suggests fundamental gaps in our understanding of gravity, space-time geometry, or the initial conditions of the cosmos itself. Deep within the vast cosmic web that structures our universe, filaments of galaxies and dark matter stretch across incomprehensible distances, forming an intricate three-dimensional network that connects galaxy clusters like threads in an immense tapestry. What remains profoundly puzzling is the discovery that these cosmic filaments exhibit magnetic fields of surprising strength and organization, fields that appear to span millions of light years while maintaining coherence that our current understanding of magnetohydrodynamics struggles to adequately explain. Observations from radio telescope surveys reveal that these magnetic fields are not random or chaotic, as one might expect from the violent processes of the early universe, but rather they demonstrate a peculiar alignment and structure that suggests an underlying organizing principle we have yet to fully comprehend. The magnetic field strengths detected within these cosmic filaments range from microgauss measurements, which, while small by terrestrial standards, represent an enormous amount of total magnetic energy given the vast volumes they occupy. These fields appear to be preferentially aligned along the filament structures themselves, running parallel to the strands of matter, as though some unseen force has systematically organized them into this configuration. Current theoretical models propose that these fields originated during cosmic inflation or were amplified through dynamo mechanisms within the early universe. Yet neither explanation fully accounts for the observed coherence and strength, particularly given the chaotic nature of the processes that should have randomized any primordial magnetic orientation. The psychological challenge in confronting this anomaly lies in our tendency to accept magnetism as a well-understood force, a phenomenon we have studied extensively in laboratories and applied successfully in technology, which creates a cognitive barrier to recognizing how little we actually understand about its behavior on cosmic scales. Deep within the cosmic void, astronomers have observed what appear to be long, delicate trails of stars stretching across the darkness between galaxies, forming structures that seem to defy the gravitational principles we have long relied upon to explain celestial mechanics. These intergalactic star streams manifest as thin filaments of stellar material that connect distant galaxies or appear to flow outward from galactic centers in organized, almost deliberate patterns, creating the visual impression of luminous rivers flowing through the infinite expanse of space. When we examine these formations through powerful telescopes, we witness stellar populations that seem to maintain coherence across distances of hundreds of thousands of light years. Yet the gravitational force required to hold such structures together would need to be exponentially more powerful than what our current models predict based on the visible matter we observe. The tidal forces at work should theoretically tear these streams apart into random distributions, scattering the stars into isolated wanderers moving independently through the void. Yet instead they remain organized, their trajectories seemingly synchronized in ways that suggest an underlying force or mechanism we have yet to fully comprehend. Our minds attempt to rationalize these streams through the lens of dark matter influence and ancient galactic collisions, proposing that the gravitational shadows of unseen matter guide and maintain these stellar pathways, an explanation that feels comforting in its logical structure, even as it requires us to invoke invisible substances to make our observations fit our expectations. We have normalized this gap between theory and observation by simply expanding our models to include unknown quantities, treating dark matter not as evidence of incomplete understanding, but as a necessary mathematical placeholder, allowing us to sleep soundly knowing that somewhere in our equations, there exists a variable we have not yet measured that explains everything. Deep within the cosmic ocean, far beyond the warm embrace of any star's gravitational influence, astronomers have discovered evidence suggesting that rogue planets, worlds cast adrift from their parent star systems, may exist in far greater numbers than previously theorized, perhaps outnumbering the planets that remain in stable orbits around stars by a factor of several times over. These wandering worlds travel through the absolute darkness of interstellar space, receiving no heat from a parent star, no light to guide them through the void, yet they continue to exist in what we might assume would be the most inhospitable environment imaginable. What makes this phenomenon particularly enigmatic is that our current models of planetary formation suggest such bodies should be far less common. They should be rare exceptions rather than the dominant population of planetary bodies in our galaxy. According to conventional planetary formation theory, planets coalesce from protoplanetary disks surrounding young stars through a process of accretion and gravitational interaction. And while some planets may indeed be ejected from their systems through gravitational encounters, the sheer abundance of rogue planets suggests either that ejection events occur far more frequently than our models predict, or that an entirely different formation mechanism is at work that we have not yet adequately understood or observed. The psychological mechanism underlying our relative indifference to this revelation involves a subtle cognitive pattern wherein phenomena that occur on scales too vast for human comprehension tend to fade from our immediate concern. And since we cannot see these worlds, cannot visit them, and cannot readily observe their individual properties, they remain abstract concepts rather than vivid realities worthy of active contemplation. In the vast catalog of celestial mysteries that astronomers have cataloged across decades of observation, few phenomena present as stark a contradiction to our current models of stellar formation as what has come to be known as the brown dwarf desert, a peculiar and seemingly deliberate absence of intermediate mass objects orbiting around stars at specific distances that should, according to all mathematical predictions and theoretical frameworks, be populated with far greater frequency than observations reveal. Brown dwarfs themselves represent a fascinating category of astronomical objects that occupy the liminal space between planets and stars, possessing enough mass to initiate deuterium fusion in their cores, yet falling short of the threshold required for hydrogen fusion that would qualify them as true stars. And yet when astronomers have surveyed the orbital regions around other stars where these objects should theoretically accumulate in abundance, They have discovered what amounts to a conspicuous void, an unexplained scarcity that defies the core assumptions embedded within planetary formation models and migration theory. The phenomenon becomes increasingly perplexing when one considers that our most sophisticated computational simulations of stellar system formation, refined through countless iterations and calibrated against numerous observational datasets, predict that brown dwarfs should occupy the space between roughly 5 and 50 astronomical units from their parent stars with considerable regularity. Yet actual surveys reveal a dramatic underrepresentation of such objects in precisely these orbital zones, a deficit that cannot be readily explained through instrumental limitations or observational bias alone. Among the thousands of exoplanets discovered orbiting distant stars, astronomers have encountered a phenomenon that fundamentally challenges our understanding of planetary formation and orbital mechanics. The existence of massive gas giant planets orbiting extremely close to their parent stars, completing full orbital cycles in just a few days, where surface temperatures would theoretically exceed thousands of degrees Kelvin, conditions that seem entirely hostile to any conventional model of planetary development. These bodies, termed hot Jupiters, should not exist according to our current theories of planetary system formation, which suggest that massive planets form in the cool outer regions of protoplanetary disks, where sufficient material and low gravitational stress allow such enormous spheres to coalesce. Yet somehow these worlds have migrated inward toward their stars, or formed there through mechanisms we have yet to fully comprehend. The leading hypothesis proposes that gravitational interactions between the developing planetary bodies within a nascent solar system cause the massive gas giants to lose orbital energy through complex three-body dynamics, spiral progressively inward, and eventually settle into these seemingly impossible close-orbit configurations that defy the orderly planetary architecture we observe in our own solar system. What remains psychologically unsettling is how readily we have accepted this explanation despite its invoking of chaotic orbital rearrangement, rather than the stable, predictable formation sequence our theoretical models originally demanded, essentially normalizing the extraordinary as merely one possible outcome of planetary migration. Among the thousands of exoplanets discovered beyond our solar system, astronomers have identified a population of worlds that should not exist in such extraordinary numbers, yet they dominate the galactic census with an almost overwhelming prevalence. These are the super-Earths and mini-Neptunes, planetary bodies that fall into a size range between our own terrestrial world and the gas giants we observe in our cosmic neighborhood, and their sheer abundance has become one of the most confounding puzzles in modern astrophysics. According to our current models of planetary formation, which emerged from studying our own solar system as a template, planets should form in a much more predictable and distributed manner across the size spectrum. Yet observations from the Kepler Space Telescope and subsequent surveys reveal that super-Earths comprise roughly 50 to 70% of all known exoplanetary systems, vastly outnumbering both smaller rocky worlds and larger gas giants in ways that contradict our most fundamental assumptions about how planetary systems assemble themselves around distant stars. The mechanism behind this mystery appears rooted in a cognitive and scientific bias that has persisted for decades, wherein we constructed our theoretical framework based on an exceptionally unusual solar system, our own, which lacks planets in this intermediate size range entirely. We assumed that our planetary architecture represented some kind of universal blueprint, when in reality it may represent an aberration, a statistical outlier that we had simply mistaken for the norm. This bias cascaded through generations of astronomical research and computational modeling, creating a self-reinforcing cycle where our predictions could not account for observations that contradicted our assumptions. The most perplexing aspect of super-Earth abundance is not merely that they exist in such profusion, but that we have normalized this contradiction without fundamentally revising our understanding of planetary accretion, migration, and system evolution. Deep within the geological and isotopic record of our planet lies a mystery that challenges our understanding of lunar formation and planetary dynamics, a phenomenon we call the Theia impact, which proposes that approximately 4.5 billion years ago, a Mars-sized celestial body collided with the proto-Earth in what would have been the most cataclysmic event in our world's history. The evidence for this event comes from multiple sources, including the unusual isotopic composition of lunar rocks brought back by Apollo missions, which demonstrate oxygen isotope ratios that are remarkably similar to Earth's own ratios, suggesting a common origin or mixing event that should not have been possible under previous planetary formation models. Scientists observe that the Moon possesses a significantly smaller iron core relative to its size compared to other terrestrial bodies, a characteristic that would make perfect sense if the Moon formed from the vaporized and ejected mantle material of Earth following a giant impact. Yet this explanation requires the hypothetical existence of Theia, a planet we have never directly observed and whose existence remains entirely inferred from circumstantial evidence. The mechanism by which we have come to accept this theory demonstrates how compelling narrative logic can organize fragmented observations into a coherent story that explains multiple phenomena simultaneously, including lunar orbital characteristics, the Earth-Moon system's angular momentum, the tilt of Earth's rotation axis, and the chemical composition of lunar samples that would be extraordinarily difficult to explain through other formation pathways. Approximately 4.1 billion years ago, during the early formation of our solar system, our planet experienced what planetary scientists call the Late Heavy Bombardment, a period of intense cosmic violence in which countless asteroids, meteorites, and celestial bodies rained down upon the inner planets with extraordinary ferocity, transforming the young Earth into a hellish landscape of impact craters, molten surfaces, and atmospheric devastation that would have rendered the planet utterly inhospitable to any form of life. The prevailing model suggests that the giant planets themselves, Jupiter, Saturn, Uranus, and Neptune, had migrated from their original orbital positions in a complex gravitational dance that destabilized the primordial asteroid belt and sent a catastrophic wave of debris cascading inward toward the terrestrial planets. Yet the precise mechanisms, timings, and causes of this planetary migration remain among the most perplexing unsolved problems in planetary science. With competing theories struggling to explain why such a cataclysmic event would occur millions of years after the solar system's initial formation rather than during it. The Late Heavy Bombardment exists in a peculiar scientific space where we observe compelling evidence of its occurrence in lunar samples, crater distributions, and isotopic dating. Yet we simultaneously lack a complete understanding of what triggered it, how long it truly lasted, whether it happened in one sustained period or multiple episodic events, and what role it ultimately played in either facilitating or preventing the emergence of life on Earth. Deep within the solar system, stretching outward from the Sun in a faint, diffuse cloud that extends far beyond the orbits of all known planets, exists a vast reservoir of microscopic particles whose origin remains fundamentally mysterious to modern astronomy. This phenomenon, known as zodiacal light dust, presents itself as a subtle luminescence visible to the naked eye under ideal conditions, appearing as a cone of faint light rising from the horizon just before sunrise or lingering after sunset, and yet despite centuries of observation and decades of advanced instrumental analysis, the precise mechanisms governing its distribution, composition, and perpetual existence continue to elude definitive scientific explanation. The dust particles themselves, believed to be remnants of cometary collisions and asteroidal erosion, scatter sunlight in ways that should, according to conventional models, result in their gradual elimination through solar radiation pressure and gravitational interactions. And yet they persist in remarkably consistent densities across vast regions of interplanetary space, suggesting either a continuous replenishment mechanism we do not fully comprehend or a fundamental misunderstanding of how these particles interact with solar forces. What makes zodiacal light dust particularly perplexing is that we have normalized its presence within our models of the solar system without truly resolving the paradoxes it presents, accepting its existence as a given, while the mechanisms that maintain this delicate equilibrium of billions upon billions of particles suspended in the vacuum remain inadequately explained. We have assigned names to the phenomenon, cataloged its properties with increasing precision, mapped its distribution across infrared wavelengths, and yet the deeper question of why this dust cloud maintains such structural coherence and density over astronomical timescales continues to haunt the discipline, suggesting that our current understanding of particle dynamics, solar-wind interaction, and interplanetary forces may be fundamentally incomplete in ways we have yet to recognize or acknowledge. Deep in the night sky, directly opposite the position of the Sun as it hangs below the horizon, there exists a faint but measurable brightening of the celestial dome known as the Gegenschein or the counterglow, a phenomenon that has puzzled astronomers and physicists for centuries despite existing in plain view above our heads. This luminous patch appears as a soft, diffuse glow approximately 10 degrees in diameter, most visible during clear nights when one travels far from light pollution, and it represents one of the most persistent mysteries in our understanding of interplanetary space and the interaction between solar radiation and the material that surrounds our world. The Gegenschein sits directly opposite the Sun in what astronomers call the antisolar point, a geometric position that should theoretically receive no direct sunlight, and yet consistently reflects a measurable quantity of light back toward observers on Earth, defying the basic expectations we hold about how light behaves in the vacuum of space. The prevailing explanation suggests that interplanetary dust particles, remnants of cometary activity and asteroid collisions distributed throughout the inner solar system, scatter sunlight back toward Earth through a process called backscattering, where particles preferentially reflect light in the direction from which it came. Yet this explanation creates as many questions as it answers, because the Gegenschein appears far brighter and more concentrated than simple statistical models of dust distribution should allow, suggesting either that our understanding of how these particles behave is incomplete, or that some additional mechanism we have not yet identified contributes substantially to the glow. Scientists have observed that the intensity and precise location of the Gegenschein fluctuates across seasons and years, variations that do not correlate cleanly with predicted changes in dust density or particle composition, indicating that forces or processes beyond our current models may be actively shaping what we observe. High above the Earth, at altitudes where few human eyes ever venture to observe, there exists a peculiar phenomenon that has captured the attention of atmospheric scientists for nearly 2 centuries, a ghostly presence that manifests itself only under very specific conditions and in very specific regions of our world. Noctilucent clouds, also known as mesospheric ice clouds, appear as delicate, silvery blue wisps that glow against the darkened evening or pre-dawn sky, yet they form at heights of approximately 80 to 85 kilometers above the surface, well into the mesosphere where temperatures plummet to nearly 120 degrees below 0 Celsius. These clouds remain largely invisible during daylight hours, yet when the sun dips below the horizon and bathes the upper atmosphere in a peculiar slant of light, these icy formations suddenly become brilliantly luminescent, creating an ethereal display that seems almost otherworldly in its delicate beauty. The profound mystery surrounding noctilucent clouds centers not merely on their appearance, but fundamentally on their origin and composition, for the mesosphere at these altitudes should theoretically be far too warm to support water-ice crystal formation, yet somehow these clouds persist and proliferate. Scientists have long puzzled over what provides the seed particles necessary for ice condensation at such heights, and the leading theories suggest either meteor dust entering from space or perhaps sulfate particles rising from volcanic activity in the lower atmosphere. Yet neither explanation fully accounts for the dramatic increase in noctilucent cloud frequency observed over the past several decades, particularly since the 1980s. Our minds normalize this phenomenon through the lens of atmospheric science and particle physics, assigning it to known processes of condensation and crystallization, yet we simultaneously struggle to reconcile its increasing prevalence with our current understanding of upper atmospheric chemistry and dynamics. Throughout recorded history and continuing into the modern era, witnesses in seismically active regions have reported witnessing unusual luminous phenomena in the sky occurring minutes to hours before significant earthquakes strike, a phenomenon that has been documented across Japan, Peru, China, and numerous other tectonically volatile areas around the world. These earthquake lights, often described as diffuse glows, flashes of blue or white luminescence, or even structured beams of light emanating from the ground or clouds, have been observed by thousands of credible witnesses, including scientists, engineers, and emergency responders who were positioned to document these events with clarity and certainty. The visual characteristics vary considerably depending on the location and magnitude of the impending seismic event, ranging from subtle illuminations that barely disturb the night sky to brilliant displays so intense they cast shadows and momentarily turn darkness into artificial daylight across entire regions. The prevailing scientific explanation centers on the piezoelectric effect occurring within mineral-rich rock formations deep beneath the Earth's surface, where the immense pressure and stress accumulated along tectonic plate boundaries causes certain crystals within the bedrock to generate electrical charges as they deform and fracture under strain. These electrical discharges theoretically ionize the atmosphere above the epicenter region, creating the luminous phenomena that observers witness from considerable distances away, a mechanism that aligns with fundamental principles of physics and materials science. Yet despite this plausible explanation gaining acceptance within seismology communities, the phenomenon remains poorly understood and inconsistently documented, with many recorded instances occurring under conditions that should theoretically render such displays impossible or invisible to the naked eye. Among the most perplexing atmospheric phenomena that scientists have attempted to explain over centuries is the appearance of ball lightning, a luminous sphere of electrical energy that manifests during thunderstorms and persists in ways that conventional electromagnetic theory cannot adequately account for. Witnesses have reported encountering these glowing orbs ranging from the size of a grapefruit to that of a beach ball, drifting silently through the air with an eerie independence from the surrounding wind patterns, sometimes passing through closed windows or solid walls without leaving any trace of damage, and occasionally emitting strange humming or crackling sounds that seem to originate from within the sphere itself rather than from any external source. The coloration varies dramatically from account to account, with observers describing brilliant whites, penetrating blues, vivid oranges, and even violet hues, and the duration of these apparitions ranges from mere seconds to several minutes of uninterrupted luminescence that casts sharp shadows on the ground despite occurring in broad daylight. The behavior of these spheres defies conventional understanding because they move with apparent purpose or intelligence, following paths that seem to trace the contours of buildings, hover near specific individuals, or navigate complex obstacles with a precision that suggests something far more complex than simple plasma ball dynamics. Scientists have proposed numerous theories to explain ball lightning, including the self-confining plasma model, the hypothesis of silicon combustion chains, exotic forms of charged particles, and hypothetical miniature nuclear reactions. Yet none of these explanations satisfactorily account for all documented observations simultaneously. On the morning of June 30, 1908, in the remote Siberian taiga near the Tunguska River, an explosion of staggering proportions flattened approximately 80 million trees across an area spanning 2,100 square kilometers. Yet no impact crater was ever discovered at the epicenter, and the precise source of this catastrophic event remains one of the most contested mysteries in modern physics and astronomy. The explosion, which released energy equivalent to 10 to 15 megatons of TNT, occurred roughly 5 to 10 kilometers above the Earth's surface, leaving witnesses miles away knocked to the ground by the shockwave. Yet when scientific expeditions finally reached the remote location years later, they found only a forest of charred trunks arranged in a radial pattern pointing away from a central point where no meteorite, no asteroid fragment, and no conventional impact debris could be found. The leading hypothesis suggests that a stony meteor or small comet airburst in the upper atmosphere, disintegrating completely from frictional heating before reaching the ground, which would explain the lack of a crater and the absence of meteoritic material. Yet alternative theories persist regarding the true nature of the phenomenon, including proposals of a massive explosion from an underground methane pocket, or even more speculative suggestions involving exotic physics that mainstream science approaches with considerable skepticism. The psychological mechanism driving our fascination with Tunguska involves the human tendency to demand physical evidence and tangible proof for extraordinary events, and when such evidence is absent, we find ourselves in an uncomfortable space where logic alone cannot satisfy our need for closure, prompting the emergence of increasingly elaborate theories to fill the void left by incomplete data and the passage of nearly a century and a half since the occurrence. Deep within the Hestelen Valley in Norway, a phenomenon has persisted for decades that continues to elude conventional scientific explanation, drawing researchers, astronomers, and curious observers to this remote mountainous region in search of answers that remain frustratingly elusive. The lights themselves appear as luminous orbs or elongated streaks that hover above the valley, sometimes remaining stationary for extended periods before suddenly accelerating to impossible velocities, defying the laws of inertia and physics as we understand them. Witnesses report that these phenomena occur with greater frequency during certain seasonal periods, particularly in the 1980s and 90s, though sightings continue to be documented into the present day, creating a persistent enigma that challenges our understanding of atmospheric phenomena and conventional physics. The lights exhibit behaviors that seem deliberately intelligent, responding to observation, changing color and intensity based on viewer proximity, and demonstrating movement patterns that suggest some form of purposeful navigation rather than random atmospheric discharge. Researchers have proposed explanations ranging from piezoelectric effects generated by mineral deposits in the bedrock to unusual plasma formations caused by specific geological and meteorological conditions. Yet none of these conventional theories adequately account for the full range of observed behaviors and the consistent witness testimonies that span generations. The psychological mechanism underlying our acceptance of these phenomena involves a kind of cognitive compartmentalization in which we recognize that something genuinely anomalous is occurring. Yet we maintain a desperate hope that future science will retroactively explain what currently defies explanation, allowing us to preserve our existing worldview without fundamental disruption. The green flash is a rare optical phenomenon that occurs during sunrise or sunset, typically visible for only 1 to 2 seconds, as the upper rim of the sun momentarily appears to glow an intensely vivid green color before disappearing below or emerging from the horizon. Observers in favorable atmospheric conditions, particularly those positioned at high elevations or near large bodies of water, report witnessing this emerald luminescence as a distinct, almost supernatural appearance that seems to defy the natural color spectrum we expect from our star. The effect has been documented across centuries of maritime records and astronomical observations, with countless credible witnesses, including scientists, pilots, and naval officers attesting to its genuine occurrence. Yet the mechanism producing this chromatic distortion remains fundamentally puzzling to conventional understanding. The atmospheric refraction that bends sunlight as it passes through increasingly dense layers near the horizon should theoretically scatter shorter wavelengths of blue and violet light more dramatically than longer wavelengths of red and orange. Yet the green flash appears to violate this principle by making green wavelengths dominant at precisely the moment when physics suggests they should be most dispersed. Standard explanations invoke Rayleigh scattering combined with atmospheric absorption and mirages, proposing that the blue light is absorbed by the atmosphere while red light is scattered away, leaving only green visible. But this explanation fails to account for the sudden intensity and saturation of the color, or why the phenomenon appears so rarely despite billions of sunsets occurring annually. The persistence of the green flash, its stubborn refusal to align perfectly with our mathematical models of light behavior, and our gradual acceptance of partial explanations that never quite resolve all observations suggest that we have normalized a celestial anomaly rather than truly understood it. Continuing to watch the skies while acknowledging that some colors our sun displays remain, at their deepest level, unexplained. High above the thunderstorms that rage across the Earth's surface, in the thin and frigid realm between the troposphere and the mesosphere, a phenomenon unfolds that challenges our understanding of electrical discharge in the atmosphere, a phenomenon known as red Sprite Lightning. These transient luminous events appear as massive, branching structures of red and crimson light that flash upward from the tops of thunderclouds, reaching altitudes of 50 to 90 kilometers into the upper atmosphere, distances that place them well beyond the conventional boundaries where we expect electrical activity to occur. The sprites themselves manifest with an otherworldly quality, their tendrils spreading outward like jellyfish tentacles or the roots of an inverted tree, glowing with an intense red coloration that seems to pulse and dance across the darkness of the upper atmosphere in patterns that remain difficult to predict or fully comprehend. These events occur in complete silence from the ground, their luminescence lasting only fractions of a second, yet their implications stretch far deeper into our understanding of planetary electrical systems. The prevailing explanation suggests that sprites form when the electrical potential between cloud tops and the ionosphere becomes sufficiently imbalanced, allowing a cascade of electrons and ions to flow upward in a phenomenon termed a transient luminous event. Yet this mechanical understanding fails to account for the complex and varied morphologies these structures display. nor does it adequately explain why some thunderstorms produce them, while others do not. Despite seemingly identical atmospheric conditions, high above the turbulent weather systems that churn across our planet's lower atmosphere, in the seemingly serene and well-understood stratosphere, observers with access to specialized equipment have documented recurring luminous phenomena that challenge our fundamental understanding of atmospheric physics and electrical discharge patterns. These events, commonly referred to as blue jets, manifest as brilliant columns of blue-violet light that extend upward from the top of thunderstorms, reaching altitudes between 30 and 50 kilometers, piercing through layers of atmosphere that should, according to conventional meteorological models, remain electrically inert and spectroscopically silent. The phenomenon was first captured on video in 1994 by accident, when researchers filming rocket launches inadvertently recorded these strange ascending luminous structures. And since that time, an accumulating body of observations has confirmed that blue jets represent a genuine atmospheric occurrence rather than instrumental artifact or misidentification of conventional lightning phenomena. The mechanism driving these events appears to involve an extraordinarily rapid electrical discharge that propagates upward from storm cloud tops, a process that operates through principles that remain incompletely characterized by contemporary atmospheric electricity research, suggesting that our models of how charge distributes and moves through the upper atmosphere contain significant gaps and oversimplifications. What renders the blue jet phenomenon particularly anomalous is that it suggests electrical potential differences and discharge mechanisms in regions of the atmosphere that our theories predict should be electromagnetically quiescent, implying that either our understanding of atmospheric ionization is fundamentally incomplete, or that some mechanism for transferring and concentrating electrical energy upward from lower altitudes operates according to principles we have not yet adequately documented or theorized. High above the Earth's atmosphere, in the thin realm between the mesosphere and ionosphere, a peculiar luminescent event unfolds with remarkable frequency, yet remains virtually unknown to most inhabitants of our planet. The Elves Ring phenomenon, discovered only in the late 1990s through satellite imagery and high-speed cameras, represents a massive, expanding ring of light that erupts outward from the upper atmosphere at speeds approaching the speed of light itself, creating a halo of electromagnetic radiation that can span over 400 kilometers in diameter within mere milliseconds. These phenomena occur in conjunction with intense lightning strikes occurring below, where the electrical discharge from cloud to ground sends a powerful electromagnetic pulse upward into the ionosphere, causing the surrounding gases to fluoresce with an otherworldly reddish or blue-white glow that expands in a perfect ring formation before fading into darkness once more. The mechanism underlying these events involves the interaction between the electromagnetic pulse generated by cloud-to-ground lightning and the ionized particles present in the upper atmosphere. As the pulse travels upward, it energizes the surrounding oxygen and nitrogen molecules, causing them to emit photons and create this spectacular but temporary light show that occurs far above human observation at ground level. What remains peculiar and somewhat unsettling about the Elves Ring phenomenon is how rarely it receives public attention or scientific scrutiny despite being a relatively common occurrence during severe thunderstorm activity, suggesting a curious disconnect between observable celestial events and widespread human awareness. The phenomenon exists in a kind of scientific blind spot, acknowledged by researchers and documented extensively in satellite archives, yet failing to capture the cultural imagination or public consciousness in any meaningful way. High above the Earth's atmosphere, satellites equipped with sensitive gamma-ray detectors have recorded thousands of intense bursts of gamma radiation emanating from within our own planetary system, events so powerful and so unexpected that they fundamentally challenged our understanding of terrestrial physics and atmospheric behavior. These terrestrial gamma flashes, first documented in the late 1990s by instruments aboard the Compton Gamma Ray Observatory, represent brief but intense bursts of high-energy photons that appear to originate from thunderstorm regions within the lower atmosphere, suggesting that the conditions within our own weather systems are capable of producing radiation typically associated with the most violent cosmic phenomena in the universe. The flashes themselves last only milliseconds, yet in that infinitesimal window of time, they release energies comparable to nuclear reactions, creating a paradox that has persisted in atmospheric science for nearly 3 decades now. What occurs within these thunderstorms appears to involve the acceleration of electrons to relativistic speeds through the intense electric fields present during severe convective activity. And when these particles achieve such extraordinary velocities, they emit gamma rays through a process known as Bremsstrahlung radiation, a phenomenon that should theoretically be impossible within the relatively modest energy densities available in terrestrial weather systems. The mechanisms that allow our planet's atmosphere to generate such violence remain incompletely understood despite extensive investigation, and our instruments continue to detect hundreds of these events each year, each one defying the conventional energy budgets that we have assigned to thunderstorm dynamics. Deep within the cosmos, rotating neutron stars known as pulsars spin with extraordinary precision, emitting beams of radiation that sweep across space like cosmic lighthouses, their rhythms so perfectly regular that astronomers have long used them as nature's most reliable clocks. Yet there exists a phenomenon that disrupts this perfect cadence in ways that current physics struggles to fully explain, and this phenomenon is known as pulsar glitches. When these ultradense stellar remnants experience what researchers call a glitch, their rotation suddenly and unexpectedly accelerates, increasing their spin rate by anywhere from a fraction of a millisecond to several full rotations per second within the span of mere seconds, as though some invisible hand has spun them faster on their cosmic axis. And what makes this phenomenon truly perplexing is that these glitches appear to violate our understanding of how a star composed almost entirely of neutron-degenerate matter should behave, for all the angular momentum should remain conserved and predictable. Yet here we observe sudden, dramatic changes that seem to emerge from nowhere. The leading theoretical explanation invokes the concept of a superfluid core within the neutron star, a region where neutrons move without friction and can possess their own distinct angular momentum separate from the outer crust. And when these two components somehow decouple and recouple, energy is released, and the observable spin increases in what scientists describe as a starquake or vortex unpinning event. Yet the exact mechanisms remain maddeningly elusive, and the precise conditions that trigger individual glitches continue to elude our most sophisticated models and observations. Deep within the cosmos exist neutron stars of extraordinary density, objects so compressed that a teaspoon of their material would weigh as much as an entire mountain on Earth. And among these remarkable celestial bodies are millisecond pulsars, rotating at rates so phenomenally fast that they complete hundreds of revolutions in a single second, with some reaching spin rates exceeding 700 rotations per second. A velocity so extreme that the equatorial surface of these objects moves at speeds approaching 20% the speed of light itself. These millisecond pulsars present a profound puzzle to astrophysicists, because according to our current understanding of stellar mechanics and the conservation of angular momentum, neutron stars should gradually slow their rotation over time as they radiate energy away through electromagnetic emissions and gravitational wave radiation. Yet these millisecond pulsars appear to have been spun up to these incredible velocities through accretion from companion stars. A process that should have definable limits, and yet continues to produce objects spinning faster than any known physical principle readily explains. The psychological comfort we derive from understanding celestial mechanics begins to fray when confronted with these objects, as our models suggest that such extreme rotation rates should generate insurmountable stresses on the stellar material itself, potentially exceeding the neutron degeneracy pressure that holds these stars together, and yet millisecond pulsars continue to exist in observable abundance throughout our galaxy and beyond. Deep within the vast cosmos, there exists a class of neutron stars that emit mysterious bursts of gamma radiation in patterns that seem to defy our most fundamental understanding of stellar physics and energy conservation. These objects, known as soft gamma repeaters, were first observed in the 1970s when astronomers detected unusual flashes of high-energy radiation coming from distant regions of space. And what made these phenomena particularly enigmatic was that the bursts appeared to repeat at irregular intervals, sometimes dormant for years before suddenly erupting with tremendous force. The most famous of these objects, SGR 1906+40, became known as the magnetar that produced one of the most powerful gamma-ray bursts ever recorded in 1998, releasing more energy in a single explosion lasting mere seconds than our Sun would produce in approximately 10,000 years. The fundamental mystery lies in the mechanism driving these releases, for while scientists have proposed that soft gamma repeaters are neutron stars with extraordinarily powerful magnetic fields, the nature of how such fields store and suddenly release such catastrophic amounts of energy remains theoretically troubling. The magnetic field hypothesis itself raises profound questions about the stability of matter under extreme conditions and whether our current models of stellar evolution and magnetohydrodynamics are genuinely complete. What persists as genuinely unsettling is that despite decades of observation and theoretical work, we cannot fully predict when these objects will burst, nor can we precisely calculate the mechanism by which magnetic energy converts into gamma radiation with such violent efficiency. These soft gamma repeaters continue to emit their mysterious signals across the electromagnetic spectrum, their behavior only partially explained by our existing frameworks, reminding us that some of the universe's most energetic phenomena continue to operate according to principles we have not yet fully comprehended or integrated into our broader understanding of cosmic mechanics and stellar behavior. Deep within the cosmos, where neutron stars and black holes engage in their eternal cosmic dance, there exists a phenomenon that continues to perplex even the most accomplished astrophysicists. The mysterious and rhythmic oscillations observed in X-ray binary systems, particularly those rapid quasi-periodic oscillations that appear at frequencies ranging from a few hertz to kilohertz ranges, defying our current understanding of how matter behaves under such extreme gravitational and magnetic conditions. When we observe these binary systems through X-ray telescopes, we witness the violent transfer of material from a companion star being pulled toward its more massive stellar companion, creating a swirling accretion disk that should theoretically produce relatively steady emissions as the material spirals inward toward the event horizon or neutron star surface. Yet instead we observe these mysterious oscillations that appear and disappear without warning, shifting in frequency and intensity in ways that our models struggle to fully predict or comprehend. The physical mechanism behind these oscillations remains frustratingly elusive, as researchers propose various competing theories involving magnetic field interactions, precession of the accretion disk, density wave instabilities, or oscillations within the inner regions of the accretion flow itself. Each theory offering partial explanations, but none providing a complete and universally accepted understanding of why such precise oscillatory behavior emerges from these chaotic environments. What makes this phenomenon particularly troubling is how we have become almost comfortable acknowledging its existence, while simultaneously admitting our fundamental ignorance about its underlying causes, accepting papers and observations about X-ray binary oscillations into our scientific literature while the core physics remains contested and unclear, as if documenting a mystery is sufficient replacement for actually understanding it. Deep within the photospheres of certain stars, particularly those categorized as red dwarfs and M-class stars, observations have revealed sudden and unexplained eruptions of energy that release more power in mere seconds than our own sun produces over an entire year, phenomena known as stellar superflares. Yet the mechanisms that trigger these cataclysmic events remain persistently obscure despite decades of astronomical scrutiny and increasingly sophisticated observational equipment. Traditional stellar physics suggests that solar flares and their more violent cousins, superflares, result from the sudden release of magnetic energy accumulated in stellar atmospheres, where twisted magnetic field lines gradually build tension until they can no longer contain the pressure and explosively reconnect in a cascade of released energy. Yet this explanation falters when confronted with the actual data. Because many stars exhibiting superflares display magnetic field configurations that appear insufficient to generate the observed energy output, suggesting either that our measurements of stellar magnetism are fundamentally incomplete, or that an entirely different mechanism is operating beyond our current theoretical framework. The phenomenon becomes more puzzling when we consider that certain stars produce superflares at regular intervals, almost rhythmically, as if responding to some external trigger or internal oscillation that we have not yet identified, while other apparently identical stars in similar conditions remain quiescent for centuries, implying that there exist variables affecting superflare production that our models have failed to account for or recognize. In the winter of 2019 and 2020, astronomers around the world noticed something profoundly unusual occurring within the constellation Orion, where one of the brightest stars in our night sky, the red supergiant known as Betelgeuse, had begun to dim in a manner that contradicted established stellar physics and forced researchers to reconsider their understanding of massive star behavior. The dimming was not subtle or gradual in the expected sense. Rather, Betelgeuse lost approximately 30 to 35% of its visible brightness over the course of several weeks, making it noticeably fainter than Rigel, another star in Orion that had always been dimmer, and creating a visual anomaly that amateur astronomers and seasoned professionals alike found deeply perplexing and worthy of urgent investigation. The star's behavior defied the standard models of stellar evolution because red supergiants like Betelgeuse should dim gradually over millennia as they age, not dramatically over the span of mere months. And while scientists proposed various explanations, including the sudden formation of dust clouds around the star or unexplained fluctuations in its photosphere, none of these theories fully accounted for the magnitude and rapidity of the observed dimming, leaving researchers uncertain about the underlying mechanisms at work. What makes this phenomenon particularly unsettling from a conceptual standpoint is that our models of stellar behavior, built upon decades of observation and mathematical refinement, appeared inadequate to predict or fully explain what we were witnessing in real time, suggesting that massive stars like Betelgeuse possess complexities and behavioral patterns that remain hidden within the gaps of our current astrophysical framework. Deep within the constellation Carina, approximately 7,400 light-years from Earth, there exists a binary star system of such violent and unpredictable nature that it challenges our fundamental understanding of stellar evolution and mass transfer dynamics. Eta Carinae, a hypergiant star paired with a companion star in an extraordinarily elliptical orbit, exhibits dramatic and irregular fluctuations in brightness that cannot be adequately explained by conventional models of binary star interaction. The system underwent a spectacular outburst in the 1800s, briefly becoming one of the brightest stars visible from Earth. Yet since that time, it has continued to demonstrate erratic behavior that defies precise prediction, with variations in luminosity, spectral characteristics, and particle emission occurring in patterns that seem almost deliberately obfuscatory to our instruments and theoretical frameworks. The primary star itself possesses a mass somewhere between 150 and 200 times that of our Sun, wrapped in a dense wind of ejected material moving at velocities exceeding 2,000 kilometers per second, creating an environment so extreme and complex that our models struggle to account for all observed phenomena simultaneously. What renders this system particularly perplexing is that despite decades of intensive observation across multiple wavelengths of the electromagnetic spectrum, from radio frequencies through visible light to powerful X-ray emissions, we have developed only partial understanding of the mechanisms driving its instability. The orbital dynamics should be well understood given the mathematical tools at our disposal, and yet the star continues to exhibit unpredictable variations in its wind properties and collision zones between the stellar outflows. Deep within the Tarantula Nebula, approximately 160,000 light-years distant from Earth in the Large Magellanic Cloud, exists a star so extraordinarily massive that its very existence challenges our most fundamental understanding of stellar formation and the laws of physics that govern the cosmos. This star, designated R136A1, represents perhaps one of the most perplexing celestial anomalies that modern astrophysics has yet encountered, for it possesses a mass estimated at more than 300 times that of our own Sun, a figure that approaches and potentially exceeds what theoretical models insist should be the absolute maximum limit for stellar mass. According to our current computational frameworks and mathematical predictions, a star of such titanic proportions should not exist in the universe as we understand it, and yet there it resides, burning with the fury of millions of suns combined, defying our most carefully constructed equations and assumptions about how matter can be assembled into stellar form. The theoretical mass limit for stars, what astronomers and physicists call the Eddington limit or the radiation pressure barrier, represents a fundamental constraint where the outward pressure of light and radiation becomes so intense that it should overcome gravity itself and prevent any further accumulation of stellar material, thereby establishing a natural ceiling beyond which no star could possibly grow. Yet R136A1 brazenly transcends these calculated boundaries, maintaining its impossible mass through means that remain inadequately explained by contemporary astrophysical theory, suggesting either that our models of stellar physics contain significant gaps in their foundational assumptions, or that phenomena we have yet to identify and characterize are actively at work within this celestial furnace. In the depths of space, there exists a theoretical stellar object so unusual and so profoundly strange that its very existence challenges our understanding of how massive stars should behave when they reach the end of their lives. And this object is known as a Thorne-Zytkow star, named after the astrophysicists Kip Thorne and Anna Zytkow, who first proposed its existence in 1975 through rigorous mathematical calculation and theoretical modeling. A Thorne-Zytkow star represents an extraordinarily rare and exotic configuration where a neutron star, one of the most dense objects in the universe, with the mass of our entire sun compressed into a sphere perhaps only 20 kilometers across, has somehow found itself embedded deep within the core of a massive red supergiant star. And the two objects exist in a state of dynamic equilibrium where the neutron star continuously accretes material from the surrounding stellar envelope, while simultaneously heating and disrupting the normal nuclear fusion processes that typically occur in such massive stars. The mechanism that creates such an arrangement likely involves a binary star system where two massive stars orbit one another in close proximity, and when the more massive companion exhausts its nuclear fuel and collapses into a neutron star, gravitational interactions and orbital decay can cause this dense object to spiral inward into the envelope of its red supergiant companion, eventually settling into the core where its immense gravity creates a region of chaotic stellar dynamics, unlike anything seen in conventional stellar evolution. Deep within the cosmos, neutron stars undergo transformations so violent and theoretically problematic that they challenge our most fundamental understanding of stellar physics, and the pathway by which a neutron star becomes a magnetar remains one of the most perplexing mysteries in astrophysics. A magnetar is essentially a neutron star with a magnetic field so extraordinarily powerful that it defies conventional calculations, possessing a magnetic field strength measured in quadrillions of Gauss, which is billions of times more intense than anything we can create in terrestrial laboratories. When we observe these objects and measure their rotational decay rates, their energetic outbursts, and their sudden spinning irregularities known as glitches, the numbers simply do not align with what our current theoretical models predict should be occurring. The standard formation pathway suggests that magnetars develop through specific evolutionary channels, either through the rapid rotation of young neutron stars, through mergers of binary systems, or through some form of magnetic field amplification mechanism during the collapse of massive stellar cores. Yet when we attempt to trace backwards from the magnetars we observe today, the mathematical trajectories become increasingly problematic and inconsistent with observed phenomena. The psychological acceptance of magnetar formation pathways reveals how deeply we have internalized incomplete models, how we continue teaching students the conventional stellar evolution diagrams with confidence despite knowing that crucial gaps exist in our understanding, and how the scientific community has developed a kind of comfortable numbness toward the disconnect between prediction and observation. When two neutron stars, each weighing as much as our sun, but compressed into a sphere no larger than a city, spiral inexorably toward one another across the vast emptiness of space, they create one of the most violent and exotic events known to physics. Yet the full mechanisms of what occurs during their collision remain profoundly mysterious and resistant to our current understanding. These objects represent the densest known form of matter in the universe, with a teaspoon of neutron star material weighing billions of tons, and as they orbit their common center of gravity, they emit gravitational waves that carry away energy with such efficiency that their trajectory becomes increasingly tighter and faster, until eventually they collide in a cataclysmic embrace. The merger itself produces electromagnetic radiation across the entire spectrum simultaneously, from radio waves to gamma rays, releasing more energy in a few seconds than our sun will produce in its entire 10 billion-year lifetime. Yet we struggle to explain how the neutron star material behaves under such extreme conditions, what happens to the fundamental forces of physics, and whether the result creates a black hole, a hypermassive neutron star, or something else entirely that our theories have not yet named. Scientists observe these events through gravitational wave detection and electromagnetic observation, watching as the collision produces exotic heavy elements like gold and platinum that scatter throughout space. Yet the behavior of matter at these densities and temperatures exceeds the predictive power of both general relativity and quantum mechanics, leaving us uncertain about the true nature of the merger process itself. When two neutron stars collide in the violent cosmic dance of a binary system merger, an extraordinary explosion occurs that we call a kilonova, and within those first few moments of unimaginable heat and pressure, something remarkable happens that still puzzles astrophysicists around the world. The collision produces an astonishing abundance of heavy elements, including gold, platinum, and other precious metals in quantities so vast that a single kilonova event can create more gold than exists in all the gold ever mined throughout human history. Yet the mechanisms that generate these specific elements in such tremendous concentrations remain profoundly uncertain and contested among researchers. The traditional nuclear physics models that we use to understand stellar nucleosynthesis, which is the process by which stars create heavier elements through successive nuclear fusion reactions, struggle to adequately explain the sheer variety and quantity of heavy elements observed in kilonova light signatures and the ejected material that follows these catastrophic cosmic collisions. When scientists analyze the spectroscopic data from kilonovae, they identify the fingerprints of elements far beyond the Iron Peak, yet the exact pathways and conditions required to synthesize these materials remain incomplete in our current theoretical frameworks, suggesting that fundamental processes in extreme nuclear physics may still elude our comprehensive understanding. What we have normalized in modern astrophysics is the acceptance that kilonovae likely represent the primary cosmic factories for rapid neutron capture processes, creating the R-process elements that populate our periodic table, and yet this normalization masks a deeper discomfort with how little we truly understand about the quantum mechanics operating under such extreme densities and temperatures, where matter behaves in ways that defy easy prediction or explanation, leaving us with observations that outpace our theoretical capacity to fully comprehend them. Deep within the cosmic laboratory where light bends around massive objects, astronomers have encountered persistent irregularities that refuse to align with our current theoretical models of gravity and spacetime. Anomalies that suggest something fundamental may be missing from our understanding of how the universe actually works. When light travels across vast distances through the cosmos, the immense gravitational fields of galaxy clusters and supermassive objects curve the very fabric of space itself, causing distant light rays to bend and magnify in patterns that should be entirely predictable according to Einstein's general relativity. However, observations made through our most sophisticated telescopes have revealed that certain gravitational lensing events produce distortions that are either far more pronounced than calculations suggest they should be, or conversely, far less pronounced than the visible mass of the lensing object would seem to require. These anomalies manifest in multiple ways. Einstein rings that appear asymmetrical when they should be perfectly symmetric, magnification factors that deviate significantly from theoretical predictions, and unexpected multiple images of the same distant object appearing in configurations that contradict established models of light bending through curved spacetime. Scientists initially attributed many of these peculiarities to the presence of dark matter, that invisible gravitational substance hypothesized to comprise roughly 85% of all matter in the universe. Yet the distribution of dark matter inferred from lensing observations frequently does not align with the patterns we would expect based on other observational methods and computational models. The psychological mechanism at work here involves our deep reliance on mathematical frameworks that have proven extraordinarily successful in other domains, creating a cognitive bias toward assuming that any deviation from prediction must result from incomplete data rather than incomplete theory. Deep within the cosmic microwave background radiation that fills all of space, a radiation so ancient it was born merely 380,000 years after the Big Bang itself, scientists have detected persistent irregularities and anomalies that resist conventional explanation within our current frameworks of cosmological understanding. When researchers first mapped this primordial radiation with unprecedented precision using satellites like WMAP and the Planck Observatory, they expected to find a relatively uniform distribution of temperature variations corresponding to the density fluctuations that would eventually give rise to galaxies and cosmic structure. Instead, they discovered unexpected asymmetries in the distribution of temperature anisotropies, with certain regions of the sky appearing systematically hotter or colder than our theoretical models predict, and these cold spots and warm spots persisting in patterns that seem far too organized and coherent to emerge from random quantum fluctuations alone. The psychological mechanism that allows us to continue observing these irregularities without fundamentally questioning our understanding of cosmic origins relates to our tendency to compartmentalize unexplained phenomena within the framework of incomplete data or instrumental limitations, assuming that further refinement of our tools and observations will eventually resolve the discrepancies into patterns we can comfortably explain. We tell ourselves that perhaps the universe is simply more complex than our models account for, or that some unknown systematic error in our measurements has introduced artificial patterns, or that sufficient time and better telescopes will reveal the mundane explanation lurking beneath what currently appears anomalous.